Deep within our galaxy's heart beats something terrifying. An invisible giant lurks there, possessing the gravitational strength of 4 million blazing suns combined. This cosmic predator goes by the name Sagittarius A star, representing one of nature's most fearsome creations, a supermassive black hole. While its distant cousins fuel brilliant quasars across the universe, our galactic beast remains eerily quiet. Yet this deceptive calm masks an underlying fury of twisted space-time, magnetic tempests, and gravitational forces so intense they warp reality itself. Humanity's quest to unveil this monster reads like a detective thriller spanning centuries. We had to pierce through veils of cosmic debris, decode invisible signals, and develop revolutionary technologies just to glimpse what was always hiding in plain sight. This journey transformed our understanding of everything MIRTS, from how galaxies form to the fundamental nature of space and time. Behind layers of stellar fog sits the most crowded neighborhood in our entire galaxy. Astronomers call this region the galactic bulge, a massive spherical swelling containing hundreds of billions of ancient stars. From Earth's perspective, this stellar metropolis blocks our view toward the galaxy's true center like an impenetrable wall of light and shadow. Early stargazers faced an impossible challenge. When they aimed their primitive telescopes towards Sagittarius constellation, they encountered total chaos. Countless stars blended together into an indecipherable mess, broken only by serpentine dark lanes snaking through the brightness. These weren't empty voids, but rather dense clouds of microscopic particle modest carbon grains, ice crystals, and rocky debris left behind when ancient stars died explosive deaths. These cosmic dust particles, though individually tiny, spread across such vast distances that they create an effective barrier against visible light. Imagine trying to see through a sandstorm stretching for thousands of light years. That's exactly what confronted every astronomer who dared to peer toward our galaxy's heart. The Milky Way's structure itself conspired against discovery. While most of the galaxy spreads out in a thin disk resembling a cosmic pancake, the central bulge swells outward like a balloon. Within this inflated region, stars crowd together at densities unimaginable in our solar neighborhood. They overlap, interfere with each other's light, and create a bewildering tapestry that defied interpretation for generations. This stellar traffic jam generated another problem. Stars within the bulge don't leisurely orbit, like planets around the sun. Instead, they race through their paths at breakneck speeds, following complex elliptical trajectories that require years of patient observation to decode. Without modern computer analysis, tracking these motions proved nearly impossible. For centuries, astronomers remained completely unaware of what they were missing. Some prominent scientists even believed our sun occupied a central position within the galaxy. When they counted stars in all directions and found roughly equal numbers everywhere, they concluded we must be sitting near the middle. They couldn't have been more wrong that the dust clouds had created this illusion by hiding the galaxy's true structure. William Herschel, one of history's greatest astronomers, spent decades attempting to map the Milky Way using nothing but star counts. He meticulously catalogued thousands of celestial objects, trying to deduce our galaxy's shape by analyzing where stars appeared most numerous. But Herschel lived before anyone understood interstellar extinction, the way dust dimmed and obscured distant stars. His maps, though beautifully crafted, bore little resemblance to reality. The breakthrough came only when scientists realized they needed to abandon visible light entirely. If dust blocked ordinary starlight, perhaps other forms of electromagnetic radiation could penetrate where human vision failed. Infrared light, with its longer wavelengths, proved capable of threading through cosmic debris that completely blocked optical telescopes. Radio waves offered even greater penetrating power. These invisible signals could traverse the entire galaxy with minimal interference, carrying information from the most distant and obscured regions. When radio astronomy emerged in the mid-20th century, it revolutionized our understanding of cosmic structure. The first hints of something extraordinary came in the 1930s, when Carl Jansky detected mysterious radio emissions from Sagittarius. This wasn't the gentle whisper of ordinary stars, but rather a powerful beacon broadcasting from the galaxy's core. Scientists designated this source Sagittarius A, marking the beginning of a decades-long investigation into its true nature. As radio telescopes grew larger and more sensitive, the signal resolved into components. The strongest emission came from an incredibly compact region that astronomers eventually labeled Sagittarius A star. Here was something unlike anything previously encountered, a radio source smaller than our solar system, yet outshining entire star clusters. Meanwhile, infrared astronomy began revealing the hidden stellar population surrounding this enigmatic object. Specialized detectors sensitive to heat radiation could peer through dust clouds that remained opaque to visible light. For the first time, scientists could observe individual stars orbiting near the galactic center and measure their motions with unprecedented precision. What they discovered defied explanation using conventional stellar physics. Stars closest to Sagittarius A star moved at velocities approaching 10,000 kilometers per second, to speeds that should have torn apart any normal gravitational system. Yet these stellar speedsters followed perfectly predictable elliptical orbits, as if guided by an invisible hand of immense gravitational strength. Only one explanation fit the observations. Hidden within that tiny radio source lurked a gravitational monster so massive that even light itself couldn't escape its grip. The evidence pointed inexorably toward a supermassive black hole, the region where matter had collapsed so completely that it created a permanent tear in the fabric of space-time. But proving this required revolutionary new techniques. Scientists needed to track individual stars over many years, accumulating enough orbital data to calculate the central mass with confidence. They had to develop adaptive optics systems capable of correcting atmospheric turbulence in real time. Most challenging of all, they eventually needed to photograph the unphotographable, MINUSO capturing an image of the black hole's shadow against the glowing plasma surrounding it. This cosmic detective story spans from ancient mythology to cutting-edge physics, from the first crude telescopes to space-based observatories worth billions of dollars. Along the way, it has revealed not just the monster at our galaxy's heart, but fundamental truths about how the universe itself operates. Sometimes the greatest discoveries emerge from the most mundane tasks. In 1931, a brilliant young engineer named Carl Jansky found himself wrestling with an annoying technical problem that would accidentally unlock the universe's deepest secrets. Working at Bell Telephone Laboratories in New Jersey, Jansky had been assigned a seemingly routine mission: eliminate mysterious interference plaguing long-distance radio communications. The radio industry was exploding across America. Ships navigated by wireless signals, broadcasting stations filled the airwaves, and international communication depended on crystal-clear transmissions. But persistent static kept disrupting these vital connections, creating crackling background noise that engineers couldn't explain or eliminate. To hunt down these phantom signals, Jansky constructed an unusual contraption that became legendary in scientific circles. His rotating antenna array, nicknamed the merry-go-round for its circular track system, could pivot to scan every corner of the sky. This mechanical marvel operated at 20.5 MHz, capturing radio frequencies invisible to human senses, yet perfect for long-range communication studies. Month after month, Jansky meticulously documented every burst of interference. Most sources proved mundane nearby thunderstorms generated atmospheric crackling, while distant lightning strikes produced sporadic pops and hisses. But one mysterious signal defied explanation. This persistent hum appeared with clockwork regularity, cycling through a predictable 24-hour rhythm that initially suggested solar origin. However, careful timing measurements revealed a crucial discrepancy. The signal arrived approximately 4 minutes earlier each successive day, night a pattern that matched Earth's rotation relative to distant stars rather than our sun. This subtle shift provided the smoking gun evidence that the transmission originated far beyond our solar system, somewhere deep within the Milky Way's stellar realm. The direction proved even more intriguing. Jansky's measurements consistently pointed towards Sagittarius constellation, precisely where the galaxy's center lies hidden behind veils of cosmic dust. Humanity had just received its first deliberate message from interstellar space, though delivered through pure serendipity rather than intentional exploration. This groundbreaking revelation initially generated little enthusiasm within astronomical circles. Most scientists remained fixated on traditional optical observations, Viewing radio waves as mere curiosities rather than revolutionary research tools, Bell Laboratories, focused on practical communication solutions rather than cosmic mysteries, reassigned Jansky to other projects. His pioneering antenna was eventually scrapped, its historic importance unrecognized until decades later. But revolutionary ideas rarely die quietly. Gurot Rieber, a passionate radio engineer and amateur astronomer from Illinois, recognized the profound implications of Jansky's work. In 1937, Rieber constructed the world's first purpose-built radio telescope in his suburban backyard via a 9-meter parabolic dish that shocked neighbors and inspired scientists worldwide. Working alone with minimal funding, Rieber conducted the first systematic radio survey of our galaxy. His homemade instrument confirmed Jansky's discoveries while revealing an entirely invisible universe. Celestial objects that appeared dim or completely dark through optical telescopes blazed with intense radio emissions. The galactic center, perpetually shrouded in dust clouds, suddenly became one of the brightest beacons in radio wavelengths. World War II temporarily diverted attention from peaceful astronomical research, but radar technology developments during the conflict inadvertently advanced radio astronomy capabilities. Military engineers created increasingly sophisticated detection systems, many of which found civilian applications once hostilities ended. The 1950s witnessed explosive growth in radio telescope construction. Scientists built larger dishes with enhanced sensitivity across broader frequency ranges. These technological marvels unveiled phenomena that challenged fundamental assumptions about cosmic structure and behavior. Gas clouds invisible to optical instruments glowed magnificently at radio wavelengths. Supernova remnants, stellar nurseries, and even distant galaxies broadcast distinctive signatures across space. Yet that original signal from Sagittarius remained particularly fascinating. Now designated Sagittarius A, this compact radio source occupied an incredibly tiny region while generating enormous power output. Unlike diffuse nebulae or extended star-forming regions, this beacon appeared point-like even through the most advanced instruments available. Such characteristics suggested something extraordinary, an object simultaneously minuscule by galactic standards, yet capable of producing radio emissions visible across tens of thousands of light-years. No known stellar phenomenon could explain such extreme properties. Scientists realized they were confronting something completely unprecedented in their understanding of cosmic physics. However, solving this mystery required patience and technological advancement far beyond 1960s capabilities. The galactic center sits 26,000 light-years from Earth, a distance so vast that even rapidly moving stars appear nearly stationary from our perspective. Tracking orbital motions around the mysterious radio source would demand decades of precise measurements using instruments not yet invented. Meanwhile, another revolution was quietly brewing in observational astronomy. Scientists began developing detectors sensitive to infrared radiation, heat signatures invisible to human eyes, but capable of penetrating dust clouds that completely blocked visible light. This technology promised to finally pierce the veil surrounding our galaxy's heart. Early infrared astronomy required extreme creativity. Earth's atmosphere absorbs most heat radiation before it reaches ground-based telescopes, forcing researchers to launch instruments on high-altitude balloons or aircraft flying above the thickest atmospheric layers. These challenging observations provided tantalizing glimpses of hidden stellar populations, but lacked the resolution and sensitivity needed for detailed studies. The solution involved building observatories on remote mountaintops where thin, dry air minimized atmospheric interference. Mauna Kea in Hawaii and Chile's Atacama Desert became premier sites for infrared telescopes, their extreme altitudes and desert conditions creating near-space observing environments. From these elevated vantages, astronomers obtained their first clear infrared views of the galactic center. Regions appearing completely blank in optical photographs suddenly teemed with stellar activity. The galaxy's heart wasn't empty darkness, but rather a bustling metropolis of ancient stars hidden behind interstellar fog. Still, ground-based observations faced fundamental limitations. Earth's-own thermal emissions and residual atmospheric absorption continued hampering certain infrared wavelengths, crucial for galactic center studies. The ultimate solution required escaping our planet's interference entirely. NASA's 1983 launch of the infrared astronomical satellite marked another watershed moment. Though IRAS conducted an all-sky survey rather than focusing specifically on the galactic center, it demonstrated space-based infrared astronomy's revolutionary potential. Previously invisible cosmic structures blazed with thermal emissions, revealing star formation regions, planetary nebulae, and galactic dust lanes with unprecedented clarity. The 2003 Spitzer Space Telescope represented the next quantum leap. Operating far from Earth with instruments cooled to near absolute zero, Spitzer achieved sensitivity levels impossible for ground-based facilities. Its infrared vision could detect individual stars orbiting dangerously close to the mysterious radio source, finally providing the observational tools needed to unravel the galactic center's deepest secrets. Simultaneously, ground-based infrared technology continued advancing. Competing research teams at Chile's Very Large Telescope and Hawaii's Keck Observatory began marathon observing campaigns, tracking stellar motions near Sagittarius A star with extraordinary precision. These patient investigators would spend years following the same stars, accumulating orbital data that would ultimately prove the existence of our galaxy's central monster. The breakthrough came through watching cosmic ballet performers execute their death-defying choreography around an invisible partner. These stellar dancers, designated with simple names like S-stars, would become the key witnesses in one of astronomy's greatest detective stories. Among them, a particular star designated S2 emerged as the smoking gun evidence that would finally solve the mystery lurking at our galaxy's heart. TAS2 follows an extreme elliptical trajectory that carries it perilously close to the enigmatic radio source known as Sagittarius A star. During its closest approach, this stellar daredevil plunges to within just 120 times the distance between Earth and our Sun, practically grazing the event horizon of whatever monster lurks there. At such proximity, S2 accelerates to mind-bending velocities exceeding 5,000 kilometers per second, fast enough to traverse the Earth-Moon gap in barely 60 seconds. Two rival research teams embarked on separate quests to decode these stellar movements, each employing cutting-edge technology and extraordinary patience. Reinhard Genzel's group, operating from Germany's Max Planck Institute, devoted decades to this cosmic surveillance project. Simultaneously, Andrea Gheze's team at UCLA launched their own independent investigation, creating healthy scientific competition that would ultimately validate their remarkable findings. Both teams faced seemingly impossible technical challenges. Even the world's most powerful ground-based telescopes struggled against Earth's atmospheric interference, which constantly distorts celestial images and makes precise measurements nearly impossible. Stars appear to dance and shimmer due to turbulent air currents, creating false motions that can easily mask genuine orbital behavior. The solution required revolutionary adaptive optics, technology's sophisticated systems that monitor atmospheric disturbances hundreds of times per second, and instantly adjust telescope mirrors to counteract these effects. These real-time corrections transform blurry, dancing star images into razor-sharp points of light, enabling astronomers to track stellar positions with unprecedented precision. Through their infrared instruments equipped with these adaptive systems, both research groups began following SINJ-2's orbital journey with obsessive dedication. Year after year, they accumulated positional measurements, slowly piecing together the star's complete trajectory around the invisible gravitational anchor point. The work demanded extraordinary persistence. MICE-2 requires 16 Earth years to complete one full orbit, meaning researchers had to maintain their vigil across nearly 2 decades. The payoff proved spectacular. SAGE-2's path traced a perfect ellipse in space, following gravitational laws with mathematical precision. By applying centuries-old orbital mechanics principles, first developed by Johannes Kepler, astronomers could calculate the exact mass required to generate such stellar motion. The result sent shockwaves through the scientific community. Whatever was pulling ZAG-2 through its breakneck orbit possessed approximately 4 million times our Sun's mass, yet occupied a region smaller than our entire solar system. No known stellar configuration could explain such extreme mass concentration. Only one theoretical object matched these impossible characteristics: the supermassive black hole. This represented far more than mere academic curiosity. For the first time in history, scientists were directly observing stellar orbits around a suspected black hole in real time. Previous black hole studies relied on indirect evidence, mysterious X-ray emissions from distant galaxies or theoretical computer simulations. Here, astronomers could watch actual stars performing gravitational ballet around an authentic cosmic monster. The evidence strengthened with each passing observation season. Additional CES stars were identified and tracked, each following its own distinctive orbital path around the same central point. Some traveled longer, slower trajectories that took decades to complete. Others ventured even closer than S2, experiencing gravitational forces that stretched the boundaries of known physics. Most remarkably, these stellar orbits displayed subtle deviations that couldn't be explained using Isaac Newton's classical gravity equations. The paths showed tiny shifts and timing variations that precisely matched predictions from Albert Einstein's general relativity theory. This meant the gravitational field near Sagittarius A star was so intense, it was literally warping the fabric of space-time itself. In 2002, Andrea Ghe's team published their groundbreaking analysis of S2's complete orbital cycle, providing the first definitive proof of a supermassive black hole at our galaxy's center. 6 years later, Reinhard Genzel's group released their own independent measurements, reaching virtually identical conclusions despite using different telescopes and analysis techniques. The scientific consensus became overwhelming. Molso Galaxy harbors a 4 million solar mass black hole. Technological advances continued enhancing observational precision throughout the following decade. By 2010, astronomers could measure stellar positions to within thousandths of an arc, second Balyard to detecting a human hair's width from several kilometers away. These extraordinary capabilities revealed even more S-stars and refined mass calculations with unprecedented accuracy. Yet despite this triumph of observational astronomy, one crucial element remained elusive. While scientists could track the gravitational footprints and study the orbital evidence, the black hole itself remained completely invisible. They had mapped its influence, calculated its mass, and proven its existence, but the actual object continued hiding behind its own light-trapping event horizon. Understanding Sagittarius A star requires recognizing its place within the broader family of cosmic vacuum cleaners that populate our universe. Black holes come in multiple varieties, each with distinct formation mechanisms, sizes, and behaviors that paint a comprehensive portrait of these gravitational extremes. The smallest family members, stellar mass black holes, emerge from the catastrophic deaths of heavyweight stars. When massive stellar giants exhaust their nuclear fuel reserves, they can no longer maintain the delicate balance between outward radiation pressure and inward gravitational collapse. The core implodes with unimaginable violence, crushing matter to densities beyond human comprehension. If the collapsing star contains enough mass, typically 8 to 25 times our sun's weight, the implosion creates a stellar mass black hole. These objects pack enormous mass into incredibly compact spaces, sometimes measuring only a few dozen kilometers across, while containing more material than our entire solar system's central star. Though relatively small by cosmic standards, stellar mass black holes can dramatically affect their neighborhoods. When paired with normal companion stars, they can strip material away through gravitational theft, creating brilliant accretion disks that shine intensely in X-ray wavelengths. Astronomers have identified dozens of these cosmic vampires throughout our galaxy by studying their distinctive energy signatures. Between stellar mass objects and supermassive giants lies a mysterious intermediate category that continues puzzling researchers. These medium-sized black holes contain hundreds to thousands of solar masses, occupying an apparent gap in the cosmic hierarchy. Their formation mechanisms remain poorly understood, though several theories attempt to explain their existence. Some intermediate mass black holes might form through collisions between smaller stellar mass objects within dense globular clusters, where thousands of stars crowd together in relatively tiny volumes. Others could represent primordial remnants from the early universe, formed through different processes than their modern stellar mass cousins. These mysterious middleweight objects might serve as crucial missing links in black hole evolution, potentially growing over cosmic timescales into the supermassive monsters found at galactic centers. If this growth pathway proves correct, intermediate mass black holes could be evolutionary stepping stones connecting the smallest and largest varieties. At the cosmic heavyweight championship level sit supermassive black holes like Sagittarius A star. These giants contain millions or billions of solar masses, with some reaching truly staggering proportions. The largest known specimen, Ton 618, contains an estimated 66 billion times our Sun's mass, a number so large it defies meaningful comprehension. How such enormous objects formed remains one of astronomy's greatest unsolved mysteries. Current theories propose several pathways, each with compelling evidence and significant challenges. Perhaps supermassive black holes grew from smaller seeds over billions of years, gradually consuming surrounding matter until reaching their current gigantic proportions. Alternatively, they might have formed during the universe's earliest epochs, through direct collapse of massive primordial gas clouds, bypassing the normal stellar evolution process entirely. This would explain how supermassive black holes existed when the universe was less than 1 billion years old, seemingly insufficient time for growth from stellar mass seeds. Recent discoveries have revealed that virtually every large galaxy contains a central supermassive black hole, suggesting these objects play fundamental roles in cosmic evolution. The masses of galactic central black holes correlate remarkably well with properties of their host galaxies, indicating deep connections between black hole growth and overall galactic development. This relationship implies that supermassive black holes aren't merely passive residents of galactic centers, but active participants in cosmic evolution. Their gravitational influence and energy output can regulate star formation across entire galaxies, creating feedback mechanisms that shape galactic structure and composition over cosmic time. Sagittarius A star represents a relatively quiet example of this supermassive family. Unlike the brilliant quasars powered by actively feeding black holes in distant galaxies, our galactic center remains surprisingly subdued. It occasionally flares with increased activity when consuming small amounts of nearby material, but generally maintains a low profile compared to its more boisterous cousins. This relative tranquility makes Sagittarius A star an ideal laboratory for studying black hole physics without the complications introduced by violent accretion processes. Scientists can observe the pure gravitational effects on nearby stars and gas, without interference from the intense radiation fields that characterize actively feeding supermassive black holes. The diversity within the black hole family demonstrates these objects' fundamental importance in cosmic architecture. From stellar remnants to galactic anchors, they represent gravity's ultimate expression and continue revealing new insights about the universe's most extreme physical conditions. At the apex of gravitational dominance stand the true titans, supermassive black holes, containing millions to billions of solar masses, compressed into regions that would fit comfortably within our solar system's boundaries. Sagittarius A star, despite being considered lightweight within this elite category, still commands gravitational authority that dwarfs human imagination by factors of 4 million. Unlike their stellar mass cousins born from individual dying stars, these cosmic leviathans couldn't have emerged through single catastrophic events. Their formation required patient accumulation across cosmic ages, possibly beginning with massive primordial gas cloud collapses during the universe's infancy, or through gradual merging of smaller black holes within dense stellar neighborhoods. Nearly every major galaxy harbors one of these central monsters, suggesting they play crucial architectural roles in cosmic evolution. Their gravitational influence extends far beyond their immediate vicinity, orchestrating stellar motions and gas flows across entire galactic domains, while regulating star formation through complex feedback mechanisms. Theoretical physics proposes even more exotic varieties that exist only in mathematical frameworks. Primordial black holes represent perhaps the most intriguing possibility, objects formed not through stellar death, but from extreme density variations during the universe's first moments after the Big Bang. These ancient relics could range from asteroid-sized miniatures to supermassive giants, potentially scattered throughout space like invisible cosmic mines. If primordial black holes exist in significant numbers, they might occasionally drift through our solar system undetected, their presence revealed only through subtle gravitational perturbations or rare collision events. Some researchers speculate that unexplained astronomical phenomena minus mysterious gamma-ray bursts or dark matter interactions could result from encounters with these primordial wanderers. At the extreme upper end of the mass spectrum lurk ultramassive black holes exceeding 10 billion solar masses. These rare behemoths occupy the centers of the universe's largest elliptical galaxies, raising fundamental questions about growth rate limits and maximum achievable black hole masses. Their existence challenges our understanding of how quickly these objects can consume surrounding matter without disrupting their own feeding processes. Sagittarius A star occupies a relatively tranquil position within this supermassive family tree. While many of its cousins power brilliant quasars visible across billions of light years, our galactic center maintains a surprisingly low profile. These active galactic nuclei consume material at prodigious rates, generating blazing jets and intense radiation that outshine entire galaxy populations. Our local monster currently operates in energy-saving mode, only occasionally flaring when small amounts of nearby gas or debris venture too close to its event horizon. These brief feeding episodes produce temporary brightening across radio, infrared, and X-ray wavelengths before settling back into relative dormancy. This peaceful behavior creates both advantages and challenges for scientific study. Without the overwhelming radiation signatures characterizing active black holes, researchers can observe pure gravitational effects on nearby stars and gas, without interference from chaotic accretion processes. However, the lack of continuous bright emissions also makes certain measurements more difficult compared to their hyperactive relatives. The diversity within black hole classifications demonstrates these objects' fundamental importance across all cosmic scales. Stellar remnants influence local stellar neighborhoods. Intermediate mass objects potentially serve as evolutionary bridges, while supermassive giants anchor entire galactic structures and regulate cosmic evolution over billions of years. Every astronomical discovery carries naming traditions that blend scientific precision with human creativity, and Sagittarius A star exemplifies this fascinating intersection between cosmic grandeur and practical catalog keeping. The unusual designation emerged from careful radio observations conducted during the early 1970s by astronomers Bruce Ballack and Robert Brown, who were systematically mapping mysterious signals emanating from our galaxy's heart. Working with cutting-edge radio telescopes of their era, these researchers gradually resolved what initially appeared as a single bright source into multiple distinct components clustered within the galactic center region. Following established astronomical conventions, they designated this entire radio complex as Sagittarius A, simply meaning the first significant radio emitter discovered within Sagittarius constellation boundaries. The constellation reference serves purely as a celestial address system rather than indicating any physical association with Sagittarius stars. From Earth's embedded position within the Milky Way's disk, astronomers cannot view our galaxy from external vantage points, making constellation directions essential for navigation through the three-dimensional cosmic landscape surrounding us. As Ballack and Brown refined their observations, using increasingly sophisticated radio imaging techniques, one particular component within the Sagittarius A complex demanded special attention. This central source appeared extraordinarily compact, yet incredibly powerful, radiating intense radio emissions from a region smaller than anything previously encountered in galactic astronomy. The distinctive asterisk notation attached to this source borrowed terminology from atomic physics, where similar symbols traditionally indicate excited energy states, atoms or particles containing more energy than their ground state configurations. Though not formally adopted as astronomical nomenclature, the asterisk perfectly captured this radio source's exceptional intensity and mysterious nature compared to its surroundings. The designation proved prophetic in ways Ballack and Brown never anticipated. Their excited radio source would eventually be recognized as one of nature's most extreme objects, a supermassive black hole whose gravitational field warps space-time itself into configurations that challenge human comprehension. Ironically, the word star, embedded within Sagittarius A star, represents the complete opposite of its true nature. Rather than generating light through nuclear fusion like genuine stars, this cosmic monster devours illumination entirely, trapping photons within gravitational fields so intense that escape becomes impossible. The name literally designates something that consumes starlight as a star itself. This naming paradox reflects astronomy's rich tradition of preserving historical designations, even when scientific understanding evolves dramatically. Ancient star names like Betelgeuse and Rigel originated from Arabic astronomical traditions, while modern discoveries often receive practical catalogue numbers like M87 or NGC 4472 that prioritize systematic organization over poetic inspiration. Radio astronomy developed its own naming conventions, reflecting the field's technical origins and systematic survey approaches. Most radio sources receive designations indicating their celestial coordinates, strings of numbers specifying precise positions within standardized reference frameworks. Pulsars, those rapidly spinning neutron star beacons, typically carry labels like PSRB 1919+21 that encode discovery details rather than memorable names. The Messier catalogue, compiled by 18th century comet hunter Charles Messier, numbers astronomical objects sequentially based on discovery order rather than physical characteristics or cosmic importance. Galaxy M31 in Andromeda and planetary nebula M57 in Lyra share catalogue proximity, despite representing completely different cosmic phenomena separated by vast evolutionary timescales. Modern astronomical surveys generate thousands of new designations annually, creating standardized naming systems that facilitate international collaboration while accommodating diverse discovery methods. Space telescopes, ground-based surveys, and specialized detection programs each contribute unique identifiers that help researchers track objects across multiple observational wavelengths and time periods. Professional astronomers typically employ these systematic designations in formal research communications, though popular names often emerge for objects capturing public imagination. The Hubble Space Telescope's dramatic imagery frequently inspires colorful nicknames, the Eagle Nebula, Horsehead Nebula, or Cat's Eye Nebula, that emphasize visual characteristics over technical specifications. Sagittarius A star occupies a unique position within this nomenclature landscape, combining technical precision with historical accident to create a designation both scientifically accurate and slightly whimsical. The name serves as a permanent reminder that astronomical discovery often proceeds through incremental steps, with each generation of researchers building upon previous observations while adapting naming traditions to accommodate new understanding. Today, as scientists prepare to image black holes directly and probe their immediate environments with unprecedented resolution, Sagittarius A star continues bearing its asterisk designation, a symbol that once indicated unusual radio intensity, now marking humanity's closest encounter with gravitational physics at its most extreme manifestation. The simple asterisk marking Sagittarius A star represents far more than a cosmic address. It symbolizes one of the universe's most profound mysteries. This tiny typographical symbol carries the gravitational weight of our entire galaxy, pointing toward a fundamental cosmic truth that has revolutionized our understanding of how the universe organizes itself on the grandest scales. Nearly every galaxy across the observable cosmos harbors a supermassive black hole at its gravitational heart. This isn't coincidence or statistical anomaly, that appears to be a universal architectural principle governing galactic structure throughout space and time. Spiral galaxies, elliptical giants, and even chaotic irregular systems all seem to follow this same cosmic blueprint, regardless of their individual characteristics or evolutionary histories. The first clues emerged from studying unusually brilliant galactic centers that defied explanation through conventional stellar physics. These active galactic nuclei blazed with luminosities exceeding entire star clusters by factors of millions, generating energy outputs that could only be explained through gravitational processes far more efficient than nuclear fusion. The breakthrough realization came when astronomers recognized these powerhouses as feeding supermassive black holes. As matter spirals inexorably toward these cosmic monsters, Gravitational compression heats infalling material to temperatures exceeding millions of degrees, creating brilliant accretion disks that outshine their host galaxies. This same mechanism powers distant quasars minus ancient beacons visible across billions of light years that represent the universe's most luminous persistent objects. Armed with increasingly sophisticated instruments, researchers began systematic searches for these central giants in apparently quiet galaxies lacking obvious signs of nuclear activity. Time after time, careful analysis revealed their hidden presence through subtle gravitational signatures. Not stellar velocities too high for normal galactic masses, gas clouds moving in patterns indicating invisible massive objects, and orbital dynamics pointing toward concentrated central masses. The search became a cosmic treasure hunt, with predictable outcomes. Finding a galaxy without a central supermassive black hole proved nearly impossible, shifting scientific focus from whether these objects exist to understanding why they appear universally distributed throughout cosmic structure. This discovery sparked intense theoretical investigation into galactic formation mechanisms. Perhaps supermassive black holes and galaxies emerged simultaneously during the universe's youth, forming through coordinated processes that naturally paired these gravitational anchors with their stellar collections. Early cosmic gas clouds might have collapsed directly into massive black hole seeds rather than fragmenting into individual stars, providing gravitational nuclei around which galaxies could subsequently assemble. Alternatively, the first generation of stars, one Evan, hypothetical population 3, objects far more massive than any contemporary examples, could have lived brief, violent lives before collapsing into substantial black hole seeds. These primordial remnants would then grow through billions of years of matter accumulation and black hole mergers, eventually reaching supermassive proportions. The most intriguing aspect of this cosmic pattern involves the precise relationship between central black hole masses and their host galaxy properties. Across enormous ranges of galactic size and luminosity, black hole masses correlate remarkably well with the stellar masses contained within galactic bulges, the dense central regions surrounding supermassive black holes. This correlation suggests profound evolutionary connections between black holes and galaxies that extend far beyond simple gravitational coexistence. Active black hole feeding can generate powerful outflows and jets that sweep through entire galaxies, regulating star formation by heating or expelling the raw gas needed for stellar birth. Conversely, enhanced star formation can provide more material for eventual black hole consumption, creating complex feedback loops that govern long-term galactic evolution. Yet the precise mechanisms underlying this cosmic symbiosis remain poorly understood. The chicken and egg question of which component forms first continues puzzling researchers, with observational evidence supporting multiple formation scenarios simultaneously. Timeline constraints add another layer of mystery. Astronomers have discovered billion solar mass quasars operating when the universe was less than 1 billion years old, requiring impossibly rapid growth rates, according to current theoretical models. These ancient giants must have assembled through processes fundamentally different from the steady accretion assumed by conventional black hole evolution theories. Perhaps early cosmic conditions permitted direct massive gas cloud collapse, bypassing normal stellar evolution entirely, or frequent galaxy mergers in the dense early universe could have accelerated black hole growth through repeated gravitational encounters. Each proposed solution raises new questions about the exotic physics operating during cosmic dawn. Sagittarius A star fits perfectly within this universal pattern despite its relatively modest proportions. Weighing approximately 4 million solar masses, our galactic center occupies the lightweight end of the supermassive spectrum, while still demonstrating the fundamental black hole-galaxy relationship governing cosmic structure. Some researchers speculate about exceptional cases, small, faint galaxies where no central black holes have been detected. However, instrumental limitations mean these apparent exceptions might simply harbor black holes too small or inactive for current technology to identify. As observational capabilities improve, even these outliers may reveal hidden supermassive occupants. The deeper implications extend beyond individual galaxies to cosmic evolution itself. These central engines may function as regulators controlling gas flow, star formation rates, and overall galactic morphology across billions of years. They represent silent governors influencing cosmic development, while often remaining hidden behind dust veils or dormant feeding states. Within our solar system's boundaries, Sagittarius A star would reign as an absolute destroyer. Its event horizon would engulf Mercury, Venus, Earth, and Mars before breakfast, plunging our entire planetary neighborhood into eternal darkness faster than human reflexes could register the catastrophe. Yet in the cosmic hierarchy of supermassive black holes, our galactic anchor barely qualifies as a lightweight contender. Consider M87's central black hole, the cosmic celebrity featured in humanity's first direct black hole photograph, captured by the Event Horizon Telescope in 2019. This monster contains approximately 6.5 billion solar masses. It's over 1,600 times more massive than Sagittarius A star. Its event horizon could comfortably accommodate our entire solar system, including the distant Oort cloud of comets, marking our gravitational boundary with interstellar space. Yet M87's giant doesn't even approach the upper limits of black hole gigantism, illustrating the mind-bending scale variations characterizing these cosmic extremes. The size spectrum extends far beyond anything our local experience can adequately comprehend. Home 15, A star, represents the next tier of gravitational supremacy, located over 700 million light-years away within a massive galaxy cluster. This behemoth weighs approximately 20 billion solar masses, while anchoring the largest known galaxy in the observable universe. If somehow transplanted to our galactic center, Home 15A star would fundamentally restructure the entire Milky Way through its overwhelming gravitational influence, compacting our galactic bulge into a much denser, brighter configuration while dramatically altering stellar orbital patterns throughout the galaxy. Then comes Tarn 618, a name that should invoke cosmic terror in anyone comprehending its true nature. This ultramassive monster contains roughly 40 billion solar masses, making it one of the largest black holes ever discovered. Comparing Tarn 618 to Sagittarius A star resembles comparing a skyscraper to a pebble. You could align over 10,000 copies of our galactic black hole and still fall short of matching Tarn 618's gravitational mass. The physical dimensions prove equally staggering. Light requires about 1 week to traverse Tarn 618's event horizon, compared to merely 24 seconds for our local black hole. These numbers transcend normal human comprehension, representing scales that exist purely in the realm of mathematical abstraction, rather than intuitive understanding. Paradoxically, these size differences don't necessarily translate into proportionally greater local dangers. Black hole lethality depends primarily on proximity rather than absolute mass. Their gravitational influence follows the same inverse square law governing all gravitational interactions: double the distance and reduce the force by 4 times, regardless of the central object's mass. This means replacing our Sun with an equally massive black hole wouldn't alter Earth's orbital mechanics whatsoever. Our planet would continue following the same elliptical path around an invisible gravitational anchor, though the lack of solar radiation would quickly transform Earth into a frozen wasteland. The black hole's event horizon would measure only 6 kilometers across mist far too small to affect planetary orbits directly. Galactic scale dynamics follow similar principles. Larger central black holes don't automatically consume stellar populations more aggressively than their smaller cousins. The difference lies in feeding behavior and long-term evolutionary history rather than immediate gravitational dominance. Sagittarius A star currently operates in energy conservation mode, occasionally consuming small amounts of nearby gas and debris while producing relatively modest flares across multiple wavelengths. Its feeding episodes generate brief X-ray and radio brightening events before returning to baseline dormancy, suggesting a mature, stable system that has reached equilibrium with its immediate environment. In stark contrast, Tarn 618 represents an actively feeding quasar consuming matter at prodigious rates. Its brilliant accretion disk outshines entire galaxy clusters, visible across billions of light-years as one of the most luminous persistent objects in the observable universe. This intense feeding frenzy not only powers its extraordinary brightness, but also fuels continued growth over cosmic timescales. However, our local black hole may not have always maintained such restraint. Growing evidence suggests Sagittarius A star experienced much more violent episodes in the relatively recent past, possibly within the last few million years. These active phases could have generated powerful radiation bursts sweeping across the Milky Way, potentially affecting atmospheric chemistry on planets throughout the galaxy. The mysterious Fermi bubbles provide tantalizing evidence for this hypothesis. These enormous gamma-ray emission lobes extend 25,000 light-years above and below the galactic plane, representing some of the largest coherent structures associated with our galaxy. Their energy requirements and geometric configurations suggest they originated from explosive activity at the galactic center, possibly during an ancient feeding episode, when Sagittarius A star temporarily operated as a miniature quasar. Rotational dynamics add another layer of complexity to these cosmic comparisons. Black hole spin rates influence accretion disk behavior, jet formation, and space-time geometry in their immediate vicinity. While Sagittarius A star's rotation remains under careful measurement, some larger black holes like M87's giant spin at nearly the theoretical maximum rate permitted by general relativity. This extreme rotation acts like a cosmic blender, violently churning surrounding matter while launching relativistic particle jets across thousands of light years. These spinning giants store enormous rotational energy that can be extracted through complex electromagnetic processes, providing additional power sources beyond simple gravitational accretion. TON 618's spin characteristics remain uncertain, but its massive scale and extreme activity suggest it likely harbors significant rotational energy reservoirs. The formation mechanisms required to create such monsters probably involved multiple black hole mergers during galaxy collisions, processes that would naturally impart substantial angular momentum to the final merged object. Our galactic black hole probably grew through more sedate processes: steady gas, accretion, occasional stellar consumption, and perhaps smaller black hole mergers over billions of years. Meanwhile, the cosmic giants likely required head starts through direct massive gas cloud collapse, or rapid early merger sequences during the universe's more chaotic youth. Our galactic monster didn't achieve its current 4 million solar mass status through solitary accumulation. Like most supermassive black holes, Sagittarius A star likely grew through a complex history of cosmic cannibalism, devouring smaller black holes delivered through galactic mergers spanning billions of years. The Milky Way's evolutionary story reads like a tale of gradual conquest, with our galaxy systematically absorbing dozens of smaller stellar collections over cosmic time. Each captured dwarf galaxy potentially contributed its own central black hole to our growing galactic archive. Through gravitational interactions and orbital decay, these immigrant black holes would spiral inexorably toward the galactic center, eventually merging with Sagittarius A star in violent encounters that added mass, while releasing tremendous gravitational wave signatures across space-time. This merger pathway explains how relatively modest galaxies like ours can harbor such substantial central black holes. Rather than growing exclusively through gas accretion, Sagittarius A star accumulated mass through hierarchical assembly, consuming progressively larger black holes as our galaxy grew through successive merger events. Future growth spurts await our central monster. The inevitable collision between the Milky Way and Andromeda Galaxy, scheduled to commence in approximately 4 billion years, will trigger the most dramatic feeding episode in Sagittarius A star's history. Andromeda's central black hole contains roughly 100 million solar masses, meaning our galactic merger will increase our central black hole's mass by 25 times, while creating one of the largest supermassive black holes in the local universe. These cosmic collisions also illustrate how galactic environment shapes black hole behavior across vast timescales. Sagittarius A star currently inhabits a relatively peaceful spiral galaxy filled with moderate amounts of gas and dust, surrounded by a mixture of ancient and newly formed stars. This tranquil setting contrasts sharply with the chaotic environments hosting the universe's most active black holes. TON 618 operates within a much more turbulent cosmic neighborhood, where frequent galactic interactions provide continuous streams of fresh material for consumption. Ms. 87's black hole sits at the gravitational center of a massive galaxy cluster, where regular galactic encounters and tidal stripping events deliver steady supplies of gas and stars for processing. Black holes never lose their gravitational appetite. They remain perpetually ready to consume any material venturing too close to their event horizons. The dramatic difference between quiet giants like Sagittarius A star and blazing quasars comes down entirely to available fuel supplies and feeding efficiency, rather than any inherent change in the black holes themselves. Our galactic center currently operates on starvation rations. The surrounding region contains relatively little loose gas and dust compared to the material-rich environments characterizing active galaxies. What little matter does drift toward our central monster typically gets scattered or heated through complex magnetic interactions before reaching the point of no return. Most incoming material follows chaotic orbital patterns, swirling around the black hole while gradually losing energy through friction and turbulence. However, instead of smoothly spiraling inward, much of this matter gets ejected back into space through powerful winds and magnetic field interactions. Only a thin trickle of debris actually crosses the event horizon, explaining Sagittarius A star's remarkably subdued energy output. This minimal feeding rate produces correspondingly faint emissions across all wavelengths. While detectable through sensitive instruments, Sagittarius A star's radio, infrared, and X-ray signatures remain thousands of times dimmer than typical quasar outputs. If our black hole suddenly began consuming matter at quasar-level rates, the transformation would be spectacular and potentially terrifying. A fully active Sagittarius A star would create a brilliant point source visible even during daylight hours, outshining most individual stars in our night sky. The galactic center would blaze with such intensity that casual observers could easily locate it without telescopes, fundamentally altering humanity's perception of our cosmic neighborhood. This scenario remains purely theoretical but scientifically plausible. The same physical processes powering distant quasars could operate at our galactic center given sufficient fuel supplies. The dramatic difference lies purely in environmental circumstances rather than fundamental black hole physics. The current quietude actually hindered Sagittarius A star's discovery for decades. If our central black hole had been actively feeding during the early radio astronomy era, its brilliant emissions would have been detected immediately, rather than requiring sophisticated instruments and patient observations to confirm its presence. Even at 26,000 light-years distance, an actively feeding supermassive black hole would dominate our galaxy's energy budget. This peaceful behavior tells astronomers important stories about our galaxy's recent history. The minimal activity suggests the Milky Way's central region has experienced relatively stable conditions for millions of years, lacking the violent disruptions that characterize more chaotic galactic environments. Other galaxies display dramatic evidence of recent black hole outbursts and enormous jets, stretching across thousands of light-years, expanding bubbles of superheated gas, and shock waves propagating through intergalactic space. Our galaxy shows only subtle hints of past violence, such as the mysterious Fermi bubbles extending above and below the galactic plane. However, this tranquil phase may represent only a temporary lull in Sagittarius A star's feeding cycle. Gas clouds and stellar streams continue orbiting through the galactic center, and gravitational mechanics ensure occasional close encounters with our central monster. When such events occur, brief flares of activity can illuminate the normally dark beast. Astronomers have documented several such episodes during recent decades. Sudden increases in X-ray and infrared brightness, lasting only hours before fading back to baseline levels. These momentary awakening events suggest small amounts of material occasionally breach the black hole's defenses, producing brief glimpses of the violence that would characterize continuous feeding. The most anticipated feeding opportunity came in 2014, when astronomers tracked a large gas cloud designated G2 as it approached Sagittarius A star on a collision course. Predictions suggested this encounter would trigger dramatic flares visible across multiple wavelengths, providing unprecedented observations of black hole feeding in real time. The actual event proved anticlimactic. G2 stretched and distorted under extreme tidal forces, but largely survived its close passage, with only modest increases in black hole activity. This demonstrated that even apparently promising feeding opportunities don't guarantee dramatic results, highlighting the complex physics governing material capture near event horizons. Nevertheless, the possibility remains that larger or denser clouds could trigger much more significant feeding episodes. Sufficient material influx could temporarily transform Sagittarius A star into a miniature quasar, increasing its brightness by factors of thousands while generating radiation detectable throughout our galaxy. Such events wouldn't pose direct threats to Earth given our considerable distance from the galactic center, but they would dramatically alter our night sky's appearance. The galactic center would glow intensely enough to be visible with naked eyes under dark conditions, creating a permanent bright star in the constellation Sagittarius. The current dormancy actually benefits detailed scientific study. Without overwhelming radiation from active feeding, astronomers can observe subtle processes in the black hole's immediate environment that would be completely masked by brilliant accretion disk emissions. This has enabled extraordinarily precise tracking of individual stars orbiting near the event horizon, providing unprecedented tests of general relativity in extreme gravitational fields. The quiet environment also allows detection of minor activity variations that reveal important information about black hole physics, even at minimal feeding rates. Occasional X-ray and infrared flares, though faint by quasar standards, provide crucial insights into magnetic field behavior, plasma dynamics, and particle acceleration near event horizons. There's something almost unsettling about observing such a fundamentally extreme object, maintaining such remarkable restraint. It resembles watching a cosmic predator deliberately choosing not to hunt despite abundant opportunities. This apparent contradiction between capability and behavior reflects the complex relationship between black holes and their environments. Perhaps most remarkably, this restraint may have contributed to life's development within our galaxy. Highly active supermassive black holes can generate radiation intense enough to affect planetary atmospheres across thousands of light years, potentially sterilizing worlds or preventing atmospheric retention on rocky planets. While Earth's distance from the galactic center would provide some protection from such effects, the overall habitability of our galaxy might depend partially on our central black hole's feeding behavior. The current calm represents one factor among many that has allowed life to develop and thrive throughout the Milky Way's more distant regions. The destiny of Sagittarius A star hinges largely on its ability to locate fresh sources of cosmic nutrition. While our galaxy contains abundant material, most gas and stellar components maintain stable orbits that keep them safely beyond the black hole's gravitational reach. The central region remains relatively sparse compared to the dense feeding grounds characterizing active galactic nuclei. Most stars near the galactic center follow predictable elliptical paths that carry them close enough to experience extreme gravitational forces without actually crossing the event horizon. These stellar orbits represent a delicate gravitational dance that has persisted for millions of years, with each participant maintaining sufficient velocity to avoid capture. However, galactic dynamics operate on timescales that make long-term predictions extremely challenging. Random encounters between gas clouds, gravitational perturbations from passing stars, or orbital decay through gravitational wave radiation could eventually deliver substantial meals to our patient cosmic monster. The anticipated collision with Andromeda Galaxy represents the most dramatic feeding opportunity awaiting Sagittarius A star. This cosmic collision, predicted to commence in approximately 4 billion years, will fundamentally restructure both galaxies while triggering the most violent black hole merger in our local universe's recent history. During galactic collisions, individual stars rarely experience direct impacts due to the vast empty spaces between stellar systems. However, the gravitational chaos disrupts established orbital patterns, sending clouds of gas and entire star systems on new trajectories that may carry them dangerously close to central black holes. The merger will also bring Andromeda's central supermassive black hole into direct contact with Sagittarius A star, creating a binary black hole system that will gradually spiral inward while emitting tremendous gravitational wave signals. The final merger will release more energy in gravitational waves than all the stars in both galaxies combined produce through nuclear fusion. This cataclysmic event will transform our relatively modest galactic black hole into one of the most massive objects in the local universe, potentially reaching masses exceeding 100 million solar masses. The newly enlarged black hole will occupy the center of an entirely new galaxy, likely an elliptical system formed from the merged remnants of both spiral galaxies. Before this distant merger occurs, smaller feeding opportunities may periodically activate Sagittarius A star's dormant power. Dense molecular clouds occasionally drift through the galactic center, and some may approach closely enough to trigger substantial accretion episodes. Such events could temporarily transform our quiet black hole into a brilliant beacon visible throughout the galaxy. The transformation wouldn't pose direct dangers to Earth given our considerable distance, but it would create spectacular changes in our night sky's appearance. A feeding Sagittarius A star could outshine most individual stars, creating a permanent bright object in Sagittarius constellation that would be visible even in light-polluted urban environments. These potential future scenarios remind us that cosmic tranquility rarely persists indefinitely. The universe operates on timescales that dwarf human civilization, and dramatic changes await patient observers willing to think in terms of millions or billions of years rather than human lifespans. The cosmic choreography, unfolding over the next 4 billion years, will fundamentally transform both participants in this galactic dance. When the Milky Way and Andromeda finally embrace in their gravitational waltz, the collision will unleash forces that dwarf anything our galaxy has experienced since its formation. While individual stars will mostly pass each other like ships in the cosmic night, the vast reservoirs of gas and dust distributed throughout both galaxies will experience violent disruption. Gravitational tidal forces will compress these materials, funneling enormous quantities of fuel directly toward both galactic centers in an unprecedented feeding frenzy. This influx could trigger Sagittarius A star's most dramatic transformation in billions of years, awakening it from its current dormancy into a blazing quasar phase that would fundamentally alter our galaxy's structure and behavior. The newly energized black hole would unleash powerful jets and winds capable of reshaping entire galactic regions, potentially halting star formation across vast volumes of space, while simultaneously triggering intense stellar birth in compressed gas clouds. Observations of distant galaxies provide compelling previews of such transformations. Throughout the observable universe, astronomers witness supermassive black holes cycling through periods of intense activity, followed by extended quiet phases, suggesting these giants experience multiple feeding episodes throughout their extended lifetimes. The timescales involved stretch human comprehension beyond meaningful limits. Sagittarius A star might maintain its current peaceful demeanor for another million or even 10 million years before experiencing its next significant feeding event. Alternatively, chance encounters with unusually dense gas clouds, disrupted star clusters, or wandering intermediate mass black holes could trigger dramatic outbursts within the next few million years. Black holes demonstrate cosmic patience unlike any other objects in the universe. They can endure extended fasting periods spanning millions of years without losing their fundamental capacity for violent feeding when suitable opportunities arise. This patient persistence makes long-term predictions nearly impossible, while guaranteeing that dramatic changes await observers willing to think in geological rather than human timescales. Modern astronomical instruments continuously monitor Sagittarius A star's behavior for subtle precursor signals that might herald future feeding events. Space-based X-ray observatories, infrared telescopes, and radio arrays all contribute to this ongoing surveillance, tracking minor brightness fluctuations that could indicate material beginning its final spiral toward the event horizon. Virtually every active supermassive black hole throughout the cosmos advertises its presence through brilliant accretion disks, swirling maelstroms of superheated matter that blaze with the combined luminosity of entire galaxies. These cosmic furnaces represent some of the most energetic phenomena in the universe, visible across billions of light years as they consume surrounding material at prodigious rates. Yet when astronomers focus their instruments on Sagittarius A star, expecting to find such a blazing disk announcement, they discovered something puzzling and faint. Rather than the unmistakable signature of material spiraling toward inevitable doom, our galactic center revealed only ghostly wisps of emission barely detectable above instrumental noise levels. This absence initially baffled researchers who could clearly observe abundant raw materials surrounding our central black hole. Gas clouds drift through the galactic core, dust lanes snake between stellar populations, and countless stars orbit within gravitational reach of the monster's influence. The ingredients for spectacular accretion seemed readily available, yet the expected fireworks remain mysteriously absent. The solution to this cosmic puzzle lies in understanding the delicate environmental conditions that determine whether infalling material creates brilliant displays or simply dissipates into space. Sagittarius A star appears surrounded by what specialists term a radiatively inefficient accretion flow. Technical description for material that approaches the black hole without generating significant light emission. Unlike the tightly wound, densely packed accretion disks characterizing active black holes, our galactic center hosts a much more chaotic and dispersed feeding structure. Gas molecules spiral inward, following irregular paths while experiencing constant heating through magnetic field interactions and turbulent motion. Much of this material never reaches the event horizon, instead getting ejected back into space through powerful outflows and magnetic reconnection events. The analogy resembles attempting to build an intensely hot bonfire using scattered, loosely arranged fuel rather than carefully stacked, combustible materials. While heat generation continues, the dispersed configuration prevents the concentrated energy release needed for brilliant illumination. Supply limitations compound this structural problem. Blazing quasar disks require massive, continuous material feeds to maintain their extraordinary luminosity. Active galaxies typically channel enormous gas reservoirs toward their central black holes through violent processes like galaxy mergers, intense star formation episodes, or gravitational interactions with neighboring systems. The Milky Way currently experiences none of these dramatic feeding mechanisms. Our galaxy has entered a relatively mature, stable phase, characterized by steady stellar evolution rather than the chaotic growth spurts that characterize younger galactic systems. While individual stars occasionally venture close to Sagittarius A star during their orbital journeys, no massive gas streams currently flow toward the galactic center. Evidence suggests our black hole may actually be experiencing an extended fasting period compared to its historical activity levels. X-ray observations of nearby gas clouds reveal faint echoes from ancient radiation events, indicating Sagittarius A star blazed much more brightly just a few centuries ago. These observations imply the current ghostly disk represents a gradually dissipating remnant from previous feeding episodes rather than an actively growing accretion structure. The Event Horizon Telescope's groundbreaking observations provided unprecedented insights into this mysterious feeding structure. When the Global Radio Telescope Network resolved Sagittarius A star's immediate environment, they discovered not the smooth, symmetric disk imaged around M87's black hole, but rather an irregular, patchy emission pattern that confirmed the chaotic nature of our galactic center's accretion flow. These observations reinforced theoretical models, predicting thin, hot, turbulent material flows around relatively inactive supermassive black holes. The detected emission originates from plasma heated to temperatures exceeding tens of millions of degrees, yet this superheated gas remains too dispersed to generate the brilliant radiation characteristic of more active systems. Even nearby S-stars, which approach within astronomical spitting distances of the event horizon, fail to trigger dramatic accretion episodes. Their close passages should theoretically shed material through stellar winds or tidal stripping, yet Sagittarius A star's accretion disk remains stubbornly faint. This suggests our black hole operates under highly selective feeding conditions, with magnetic fields and plasma turbulence acting like cosmic filters that deflect most approaching material. The 2014 encounter with gas cloud G2 provided a real-time test of these theoretical models. Astronomers worldwide anticipated dramatic flares when this apparently substantial gas reservoir approached Sagittarius A star on what appeared to be a collision course. Instead, the event proved remarkably anticlimactic, with G2 stretching and distorting under tidal forces while producing only modest increases in black hole activity. Subsequent analysis suggested G2 might have been a dust-shrouded star rather than a free-floating gas cloud, explaining why so little material actually reached the accretion disk. This episode highlighted the complex physics governing material capture near supermassive black holes, while demonstrating that even promising feeding opportunities don't guarantee spectacular results. Despite its overall tranquility, Sagittarius A star occasionally disrupts the cosmic peace with sudden brilliant outbursts that appear without any predictable pattern or observable trigger. These explosive flares can increase the black hole's brightness by factors of dozens within minutes, blazing briefly before fading back to baseline levels as mysteriously as they began. The unpredictability of these events makes them particularly intriguing for researchers studying black hole physics. Unlike regularly recurring phenomena that allow advanced preparation and coordinated observations, Sagittarius A star's flares strike without warning, forcing astronomers to maintain constant vigilance while hoping to catch the next episode in real time. When flares occur, they trigger frantic scientific responses as researchers worldwide redirect available telescopes toward the galactic center, racing to collect maximum data before the brightness enhancement disappears. These coordinated observation campaigns have revealed crucial insights into the extreme physics operating near our black hole's event horizon. The rapid timing of these flares provides important clues about their origin and physical scale. Events that brighten and fade within hours indicate emission sources no larger than light travel distances over those time frames, regions smaller than our solar system, yet generating energy equivalent to millions of stars simultaneously. Several competing theories attempt to explain these mysterious outbursts. The most straightforward model proposes that dense clumps of gas occasionally drift close enough to Sagittarius A star to trigger brief feeding episodes. Under normal circumstances, material around our galactic center remains too dispersed to generate significant radiation, but random density fluctuations could create compact pockets of matter that produce intense heating as they spiral toward the event horizon. Alternative explanations focus on magnetic field dynamics rather than direct material consumption. Supermassive black holes can store enormous amounts of energy within twisted magnetic field configurations that occasionally release their pent-up force through magnetic reconnection, events similar to solar flares, but operating on vastly larger scales. These magnetic explosions could generate brilliant radiation bursts without requiring new material to cross the event horizon. The most dramatic possibility involves close encounters between Sagittarius A star and nearby stellar objects or smaller black holes. Tidal forces from such interactions could strip material from approaching objects, sending debris streams spiraling toward the central monster while producing intense flashes visible across multiple wavelengths. The crowded environment near our galactic center makes such encounters statistically inevitable over long timescales, though predicting specific timing remains impossible given the complex orbital mechanics governing stellar motions in such extreme gravitational fields. The inability to predict these flares represents both a scientific challenge and an opportunity. While researchers cannot schedule observations to coincide with peak activity, the random nature of these events provides unbiased samples of black hole behavior across different environmental conditions and feeding states. Each detected flare offers a brief window into processes operating under the most extreme physical conditions accessible to human observation, regions where general relativity dominates over classical physics, and where matter approaches the ultimate point of no return represented by the event horizon. Capturing Sagittarius A star's unpredictable outbursts requires extraordinary patience combined with lightning-fast coordination across the global astronomical community. Research teams dedicate weeks to continuous monitoring, maintaining vigilant watch over our galactic center, while hoping to witness one of these mysterious brightening episodes in real time. When flares finally occur, astronomers face a frantic race against time. These events demand immediate response protocols that coordinate ground-based observatories with space telescopes, ensuring comprehensive data collection across the entire electromagnetic spectrum before the phenomenon fades back into obscurity. Success requires seamless collaboration between radio arrays, infrared detectors, X-ray satellites, and optical telescopes working in perfect synchronization. The spectral characteristics of these flares provide crucial insights into their underlying physics. Most outbursts appear strongest in X-ray and infrared wavelengths, rather than visible light, suggesting they originate from extremely hot material, operating under conditions where temperatures reach millions of degrees. Such extreme environments naturally favor high-energy emission, explaining why these events remain invisible to naked-eye observation, despite their tremendous power output. However, no simple patterns emerge from accumulated flare observations. Some episodes dominate X-ray emissions while others peak in infrared wavelengths. Duration varies dramatically, with certain events lasting mere minutes while others persist for hours before dissipating. This diversity suggests multiple physical processes contribute to flare generation, each producing distinctive signatures that reflect different aspects of black hole physics. The 2019 superflare represents the most dramatic episode ever recorded, blazing more than twice as bright as any previous event, while shocking researchers worldwide. Initial speculation focused on catastrophic scenarios like stellar disruption events, where entire stars get shredded by tidal forces before falling into the black hole. Subsequent analysis suggested a massive gas clump infalling event, possibly connected to the G2 cloud that had been drifting near Sagittarius A star for several years. This extraordinary outburst demonstrated our black hole's capacity for dramatic activity, even during its current quiet phase, raising tantalizing questions about historical feeding episodes when environmental conditions may have supported much more vigorous activity levels. Within the immediate vicinity of Sagittarius A star's event horizon, the fundamental forces governing reality shift into configurations that challenge human understanding. Gravity dominates the large-scale structure, but invisible magnetic fields create complex secondary architectures that profoundly influence how matter behaves in these ultimate extreme environments. These magnetic structures don't emerge from the black hole itself, which cannot maintain traditional magnetic fields across its event horizon. Instead, they originate from the surrounding plasma, ionized gas, whose charged particles naturally generate and sustain magnetic field configurations as they flow through the curved space-time surrounding our gravitational monster. Unlike Earth's relatively stable dipolar magnetic field generated by our planet's molten core, Sagittarius A star's magnetic environment represents pure chaos. Field lines twist, reconnect, and reconfigure constantly as plasma currents shift under the combined influences of extreme gravity, temperature variations, and turbulent motion patterns that defy conventional fluid dynamics. The Event Horizon Telescope's polarized light observations provided humanity's first direct glimpse of these invisible structures, revealing spiraling patterns in the faint emission surrounding our black hole. These observations confirm that magnetic fields near Sagittarius A star possess sufficient strength to actively shape matter, flows rather than passively responding to gravitational dynamics. This creates a fundamental competition between opposing forces operating on vastly different scales. Gravity relentlessly pulls all material toward the event horizon, following the inexorable logic of Einstein's curved space-time geometry. Magnetic fields can resist this inward flow, especially when tightly wound configurations store enormous amounts of energy that can redirect or even expel approaching matter. Such magnetic resistance may partially explain Sagittarius A star's current dormancy. If field configurations create effective barriers around the black hole, incoming material might trickle inward slowly rather than plunging directly toward the event horizon. This controlled feeding rate would naturally produce the weak emissions characterizing our galactic center's current state. However, these same magnetic structures can store tremendous energy reserves that occasionally discharge through violent reconnection events. When field lines suddenly snap and realign, they can accelerate particles to relativistic speeds while generating intense radiation bursts across multiple wavelengths. Such magnetic explosions could explain the unpredictable flares that periodically illuminate our otherwise quiet black hole. The three-dimensional architecture of these magnetic fields remains poorly understood despite advancing observational capabilities. Some theoretical models propose large-scale loop structures extending far beyond the immediate black hole environment, threading through the broader accretion flow while maintaining coherent organization across vast distances. Alternative theories suggest much more chaotic configurations, where field lines constantly break and reform in turbulent cascades that prevent stable large-scale structures from developing. Current observations hint at ordered patterns near the event horizon, transitioning to increasing disorder at greater distances, suggesting our black hole environment occupies a delicate balance between stability and chaos. This magnetic complexity may explain why Sagittarius A star lacks the prominent jets characterizing many active supermassive black holes, while other systems launch relativistic plasma beams extending thousands of light-years from their central engines. our galactic monster shows only hints of weaker, smaller-scale outflows. If magnetic fields near Sagittarius A star primarily channel energy into these modest outflows, rather than focusing it into coherent jets, this could serve as a pressure relief mechanism that prevents more dramatic feeding episodes. Material and energy that might otherwise fuel brilliant accretion displays gets redirected into these gentle winds, maintaining the black hole's current low-activity state. Near the event horizon itself, physical conditions become so extreme that conventional plasma physics models break down entirely. Magnetic fields influence charged particles through mechanisms that remain poorly understood when relativistic effects dominate particle motion. The resulting interactions can produce highly polarized radiation, whose characteristics encode information about field strength, geometry, and dynamic behavior in regions forever beyond direct exploration. The Schwarzschild radius represents one of the most elegantly terrifying concepts in modern physics, a mathematical boundary that separates the observable universe from regions forever hidden behind gravity's ultimate veil, named after German physicist Karl Schwarzschild, who derived the crucial equations just months after Einstein published his general theory of relativity. This concept defines the size of a black hole's event horizon. Schwarzschild's mathematical breakthrough came under extraordinary circumstances. Working as a soldier on the Russian front during World War I, he managed to solve Einstein's field equations for the space-time geometry surrounding a spherically symmetric mass. His solution revealed that if sufficient matter gets compressed within a critical radius, the resulting gravitational field becomes so intense that nothing, not even light itself, can escape. For Sagittarius A star, containing approximately 4 million solar masses, the Schwarzschild radius measures roughly 12 million kilometers, about 17 times our Sun's diameter. This boundary marks the event horizon, the spherical surface surrounding our black hole where the escape velocity equals the speed of light. The name event horizon captures the profound physical significance of this boundary. Events occurring beyond this radius become forever isolated from external observers, creating an information barrier that represents one of the most fundamental limits in physics. Matter, energy, and information crossing inward can never return to influence the external universe. Yet the event horizon itself represents no special physical location from the perspective of infalling matter. Objects crossing this boundary experience no sudden change in local conditions. They continue following their trajectories through curved space-time without dramatic disruption. The extreme effects associated with black holes occur much closer to the central singularity, where tidal forces become strong enough to stretch matter beyond molecular stability limits. This creates one of the most counterintuitive aspects of black hole physics. The event horizon appears as a static, well-defined boundary to external observers, yet it poses no obstacle to infalling matter. Objects can cross from the external universe into the black hole's interior, but the reverse journey becomes physically impossible once the boundary is transgressed. The mathematical elegance of Schwarzschild's solution belies the conceptual revolution it represents. His equations describe a region of space-time so severely curved that it becomes disconnected from the rest of the universe, creating an isolated pocket where different physical laws might apply and where conventional notions of causality break down. For Sagittarius A star, this event horizon remains completely invisible, despite representing one of the largest gravitational structures in our galactic neighborhood. The black hole's presence reveals itself only through its gravitational influence on surrounding matter and the faint emission from heated plasma spiraling toward the point of no return. The elegant simplicity of Schwarzschild's mathematical relationship belies the profound physical reality it describes. For any object, the event horizon radius depends solely on its total mass, creating a direct proportional relationship that links cosmic giants to stellar remnants through the same fundamental equation. Sagittarius A star's impressive mass of 8.5 forecast 10 meters kilograms, equivalent to roughly 4 million suns compressed into a single gravitational entity, produces a Schwarzschild radius of approximately 12 million kilometers. This dimension spans about 7.4 million miles, creating an invisible spherical boundary, larger than most planetary orbits yet representing an infinitesimally small fraction of our galaxy's overall scale. To appreciate this cosmic perspective, consider that Sagittarius A star's event horizon measures only 17 times our Sun's diameter. The entire boundary marking the point of no return for our galactic center could fit comfortably within the orbit of Mercury, demonstrating how these ultimate gravitational extremes occupy surprisingly compact regions compared to the stellar systems surrounding them. Yet this mathematical boundary represents far more than a simple geometric measurement. The event horizon defines a fundamental informational barrier that separates the observable universe from regions forever hidden beyond physical investigation. Everything crossing inward becomes permanently isolated from external observers, creating an asymmetric flow of matter, energy, and information that violates our everyday expectations about cause and effect. The black hole itself possesses no solid surface or physical structure that could be touched or examined through conventional means. Instead, the event horizon represents a purely geometric consequence of extreme space-time curvature, a mathematical surface where the fabric of reality bends so severely that no outward trajectories remain possible. From distant vantage points, this boundary appears as a static, well-defined sphere surrounding the central mass. However, closer inspection reveals far more complex dynamics. Space-time itself flows inward with increasing velocity as it approaches the event horizon, creating a cosmic waterfall effect where the underlying geometric structure of reality streams toward the central singularity. Time dilation effects near the Schwarzschild radius create paradoxical observation scenarios that challenge intuitive understanding. Observers falling toward the black hole experience time normally from their own perspective, yet external witnesses would see them slowing down progressively as they approach the event horizon. Light from the falling observer would redshift toward longer wavelengths while dimming until it fades beyond detection, creating the illusion that nothing ever actually crosses the boundary from an external viewpoint. The Event Horizon Telescope's groundbreaking observations provided humanity's first visual evidence of this mathematical boundary's physical reality. The famous image reveals a glowing ring of radio emissions surrounding a dark central region, not the black hole itself, but rather its shadow cast against the backdrop of luminous plasma spiraling toward destruction. This shadow appears slightly larger than the actual Schwarzschild radius, due to gravitational lensing effects that bend light rays passing near the event horizon. The true mathematical boundary lies just inside the shadow's visible edge, hidden behind the optical distortions created by extreme space-time curvature. The entire structure appears smaller in Earth's sky than a donut placed on the lunar surface would appear to terrestrial observers. Achieving sufficient resolution to image such minute details required unprecedented coordination between radio telescopes worldwide, combined with atomic clock precision and massive computational resources to process the resulting data. Beyond this visible boundary lies a realm forever closed to direct scientific investigation. According to general relativity's predictions, matter crossing the event horizon continues falling inexorably toward the central singularity, a mathematical point of infinite density, where known physics breaks down completely. Theoretical speculation about conditions within black holes ranges from conventional descriptions involving infinitely curved space-time to exotic alternatives, like Planck stars, quantum bounce scenarios, or bridges connecting to parallel universes. However, these remain purely theoretical constructs since no information can ever escape from beyond the event horizon to confirm or refute such models. The Schwarzschild radius represents more than just a boundary for light. It marks a fundamental limit for causality itself. No signal, force, or influence from the black hole's interior can ever affect external events, creating a one-way informational membrane that preserves cosmic censorship while hiding the universe's most extreme physical conditions. This informational isolation explains why black hole science must rely heavily on indirect observation methods. Researchers study orbital mechanics of nearby stars, analyze heating patterns in surrounding gas, and monitor brief flares caused by magnetic or gravitational turbulence just outside the event horizon, rather than directly examining the black hole's interior. The journey from mystery to understanding Sagittarius A star required a technological evolution spanning multiple decades, with each advancement revealing new layers of complexity while raising fresh questions about our galactic center's true nature. During the 1980s, radio astronomy dominated galactic center research as scientists refined their understanding of the persistent signal first detected by Carl Jansky decades earlier. The Very Large Array in New Mexico provided unprecedented resolution and sensitivity, confirming that Sagittarius A star represented an extremely compact yet powerful radio source with variable emission patterns that defied simple explanation. The revolutionary leap forward came through very long baseline interferometry, a technique that transforms the entire Earth into a single enormous telescope by precisely coordinating observations between radio dishes separated by thousands of kilometers. This method achieves angular resolution capabilities impossible through any individual instrument, revealing details measured in micro-arc seconds, mites, angles so small they represent the apparent size of a coin viewed from thousands of miles away. Throughout the 1990s, infrared astronomy finally matured through advances in detector technology and adaptive optics, systems capable of counteracting atmospheric turbulence in real time. These innovations allowed ground-based telescopes to achieve space-like image quality while penetrating the dust clouds that completely obscure the galactic center at visible wavelengths. The patient stellar surveillance campaigns conducted by competing research teams required extraordinary dedication and technological precision. Over decades of careful measurements, astronomers tracked individual stars following elliptical orbits around the invisible gravitational anchor, accumulating the positional data needed to calculate Sagittarius A star's mass with increasing accuracy. Space-based observatories revolutionized the field by escaping atmospheric limitations entirely. NASA's Chandra X-ray Observatory, launched in 1999, revealed that our apparently quiet black hole occasionally produces dramatic flares across high-energy wavelengths, demonstrating that significant activity continues despite the absence of obvious feeding signatures. The Spitzer Space Telescope contributed detailed infrared mapping of the crowded stellar neighborhood surrounding our galactic center, revealing complex structures and dynamics invisible through any other observational method. These space-based platforms could detect wavelengths completely absorbed by Earth's atmosphere while achieving sensitivity levels impossible for ground-based instruments. Submillimeter astronomy emerged as another crucial tool during the 2000s, operating in the electromagnetic spectrum between infrared and radio wavelengths. This region proves particularly valuable for studying cold dust and the faint emission from materials spiraling toward black holes. Arrays like the submillimeter array in Hawaii and the Atacama large millimeter array in Chile provided unprecedented resolution and sensitivity for galactic center observations. AML's high-altitude location in Chile's Atacama Desert takes advantage of extremely dry atmospheric conditions that minimize water vapor absorption, while its large collecting area and advanced interferometric capabilities enable detection of incredibly faint signals from the most distant cosmic sources. The ultimate challenge involved directly imaging the black hole's shadow, a feat requiring the most sophisticated observational techniques ever developed. The Event Horizon Telescope represents the culmination of decades of technological advancement, linking radio observatories across multiple continents to create a planet-sized telescope with resolution capabilities that seemed impossible just years earlier. The EHT network includes facilities in North America, Europe, Asia, and Antarctica, each equipped with atomic clocks providing nanosecond timing precision essential for coherent signal combination. Observations occur simultaneously across all participating telescopes, with data recorded on high-capacity storage systems for later processing through supercomputer facilities. The 2017 observing campaign targeting Sagittarius A star required unprecedented coordination between international research teams, while contending with weather conditions, equipment failures, and the complex logistics of simultaneous observations across multiple time zones. The resulting dataset contained petabytes of information requiring years of analysis through sophisticated algorithms designed to reconstruct images from sparse interferometric data. Processing Sagittarius A star's observations proved particularly challenging because the target changes appearance rapidly as superheated plasma whirls around the event horizon at relativistic speeds. Unlike the relatively stable structure observed around M87's black hole, our galactic center displays dynamic behavior that varies on timescales of minutes, requiring new analysis techniques capable of handling such temporal variability. The breakthrough image, released in 2022, represents far more than a simple photograph. It embodies humanity's first direct visual evidence of an event horizon's existence, while confirming theoretical predictions about black hole appearance developed decades before the technology existed. To test themselves, this achievement required combining observations across 4 different days in 2017, using sophisticated algorithms to identify consistent structural features while accounting for the rapid variability characterizing Sagittarius A star's immediate environment. The final image represents an average reconstruction that captures the most stable aspects of the black hole's appearance. The technological progression from Jansky's rotating antenna to the Event Horizon Telescope illustrates how scientific understanding advances through accumulated incremental improvements rather than sudden revolutionary breakthroughs. Each generation of instruments revealed new phenomena while raising questions that demanded even more sophisticated observational capabilities. Future developments promise continued advancement in our understanding of Sagittarius A star and similar objects throughout the universe. Next-generation space telescopes will provide unprecedented sensitivity across multiple wavelengths, while improvements to ground-based interferometry may eventually enable real-time movies of material flowing around black holes. The technological symphony required to study our galactic center demonstrates how modern astronomy has evolved into a collaborative international enterprise, requiring coordination between diverse institutions, funding agencies, and research communities. No single nation or organization possesses the resources necessary for such ambitious projects, making international cooperation essential for continued progress. This collaborative model has proven remarkably successful, enabling scientific achievements that seemed impossible. When individual researchers like Jansky first detected mysterious radio signals from the galactic center, the transformation from accidental discovery to detailed understanding illustrates how sustained technological development can eventually unlock the universe's most closely guarded secrets. The story of Sagittarius A star continues evolving as new instruments come online and analysis techniques improve. Each technological advancement provides fresh perspectives on this cosmic monster, while raising new questions about the fundamental physics governing the universe's most extreme environments. The culmination of decades-long technological evolution reached its crescendo in 2022 when the Event Horizon Telescope team unveiled humanity's first direct image of Sagittarius A star. This blurry yet unmistakable ring of luminous emission surrounding a dark central void confirmed theoretical predictions about black hole appearance, while providing visual proof of the event horizon's existence. The image processing required unprecedented computational sophistication, combining observations from multiple global sites through complex algorithms designed to extract coherent pictures from sparse interferometric data. Scientists had to develop entirely new techniques for handling the rapid variability characterizing Sagittarius A star's appearance, averaging observations across multiple days to identify stable structural features within the chaotic environment. This achievement represents far more than a single scientific milestone. It embodies the cumulative progress of human technological development, spanning from Jansky's accidental discovery to modern international collaborations involving thousands of researchers worldwide. Each generational advancement in instrumentation, computing power, and observational techniques contributed essential components to this ultimate success. Future developments promise even more remarkable discoveries. The James Webb Space Telescope brings unprecedented infrared sensitivity to galactic center studies, while planned upgrades to the Event Horizon Telescope network will enable sharper images and potentially real-time movies of material flowing around our black hole. The gradual unveiling of Sagittarius A star's secrets illustrates how scientific understanding advances through persistent technological development rather than sudden breakthroughs. Each improvement in observational capabilities revealed new phenomena while raising fresh questions that demanded even more sophisticated instruments and analysis methods. Gravitational lensing represents one of the universe's most elegant demonstrations of Einstein's general relativity, while providing astronomers with a natural telescope of cosmic proportions. This phenomenon occurs when massive objects warp spacetime sufficiently to bend light rays passing nearby, creating magnification and distortion effects that can dramatically enhance our view of otherwise invisible cosmic structures. The underlying physics resembles placing a heavy sphere on a stretched rubber sheet, creating a depression that deflects rolling marbles from their straight-line paths. In cosmic terms, massive objects like stars, black holes, or gas clouds play the role of the heavy sphere, while light rays follow the curved paths created by their gravitational influence on space-time geometry. For Sagittarius A star research, gravitational lensing provides multiple observational advantages that complement conventional imaging techniques. The crowded galactic center environment contains numerous massive objects that can serve as natural lenses, occasionally creating perfect alignments that magnify background sources or enhance our view of the central black hole itself. These lensing events can counteract some effects of the dust clouds that normally obscure our view toward the galactic center. When massive objects pass between Earth and Sagittarius A star, their gravitational fields can focus light rays in ways that effectively clean up the signal, providing clearer observations during brief alignment windows. Microlensing events involving individual stars orbiting near the black hole create particularly valuable opportunities for detailed study. These stellar objects can act as moving magnifiers, temporarily brightening background sources while revealing structures too faint for detection through conventional methods. The dynamic nature of the galactic center environment ensures regular occurrences of such alignment opportunities. Sagittarius A star itself serves as a gravitational lens for background objects, creating multiple images or arc-shaped distortions of distant stars. These lensing signatures provide independent measurements of the black hole's mass, while offering insights into matter distribution near the event horizon that remain invisible through direct observation. However, capturing gravitational lensing events requires extraordinary patience and continuous monitoring capabilities. The precise alignments necessary for significant lensing effects occur rarely and often last only briefly, especially given the rapid orbital motions characterizing stars near the galactic center. Global telescope networks maintain constant surveillance to ensure no opportunities are missed. The historical recognition of these phenomena developed gradually as theoretical understanding advanced alongside observational capabilities. Early radio astronomers sometimes noticed unexplained brightness variations that later analysis revealed as gravitational lensing signatures, though the tools and knowledge needed for proper interpretation weren't available at the time. Modern computational capabilities enable not only real-time identification of lensing events, but also predictive modeling based on detailed stellar motion tracking. Researchers can anticipate upcoming alignment opportunities, allowing coordinated observation campaigns across multiple wavelengths and instruments. Earth's atmosphere, while essential for sustaining life, poses formidable challenges for astronomers attempting to study fine details around Sagittarius A star. Turbulent air currents constantly bend and distort incoming starlight, creating the familiar twinkling effect visible to naked eye observers, while seriously compromising the precision measurements required for black hole research. For scientists tracking stellar orbits near our galactic center, atmospheric distortion represents more than mere inconvenience. It fundamentally limits the accuracy of positional measurements needed to calculate Sagittarius A star's mass and test general relativity predictions. Without compensation for these effects, even the most powerful ground-based telescopes cannot achieve the resolution necessary for detailed black hole studies. Adaptive optics technology revolutionized astronomical observation by directly attacking atmospheric distortion at its source rather than simply accepting these limitations. The system employs deformable mirrors that flex hundreds of times per second, counteracting atmospheric turbulence through real-time shape adjustments, guided by sophisticated wavefront sensors. The process begins with creating or identifying a bright reference point near the target object. Sometimes natural stars serve this purpose, but often astronomers generate artificial guide stars using powerful laser systems that excite sodium atoms in Earth's upper atmosphere, approximately 90 kilometers above ground level. These laser guide stars create bright reference points precisely where needed for optimal atmospheric correction. Wavefront sensors continuously analyze how atmospheric turbulence distorts light from these reference sources, feeding measurement data to high-speed computers that calculate the mirror adjustments needed to cancel out these distortions. The deformable mirror surface responds within milliseconds, maintaining sharp stellar images despite constantly changing atmospheric conditions. When adaptive optics first became available for Sagittarius A star observations, the improvement proved revolutionary. Previously blurred star fields suddenly resolved into sharp point sources, enabling the precise astrometric measurements that ultimately confirmed our black hole's existence and properties through stellar orbital analysis. The technology continues advancing with each generation of instruments. Modern adaptive optics systems achieve correction frequencies exceeding 1000 Hz while controlling hundreds of mirror actuators simultaneously, approaching the theoretical limits of atmospheric compensation possible from ground-based observatories. These capabilities enable ground-based telescopes to achieve resolution performance, rivaling space-based instruments across many observational scenarios, though at significantly lower cost, and with greater flexibility for equipment upgrades and maintenance. The combination of large collecting areas with adaptive optics correction provides observation capabilities unmatched by current space telescope designs. For Sagittarius A star research, adaptive optics enables the long-term stellar monitoring campaigns that revealed our black hole's gravitational influence through orbital mechanics analysis. Without this technology, the decade-spanning observations needed to track complete stellar orbits would have been impossible using ground-based facilities. The technology also enhances detection capabilities for the brief flares and transient events that occasionally illuminate our otherwise quiet black hole. Sharp, stable images enable more sensitive detection of brightness variations while providing better background subtraction for weak emission sources. Future developments in adaptive optics promise even greater capabilities for black hole research. Multi-conjugate adaptive optics systems correct atmospheric distortion across larger sky areas, enabling simultaneous high-resolution observation of multiple objects near Sagittarius A star. Extreme adaptive optics designs push correction capabilities toward theoretical limits, while preparing for direct detection of exoplanets around nearby stars. The success of adaptive optics for galactic center research demonstrates how technological innovation can overcome seemingly insurmountable observational challenges. What once appeared as a fundamental limitation imposed by Earth's atmosphere transformed into a solvable engineering problem through clever application of real-time control systems and high-speed computing. This technological triumph enabled ground-based telescopes to compete directly with space-based facilities for many research applications, while maintaining advantages in cost-effectiveness, upgrade flexibility, and operational responsiveness. The combination of large apertures with adaptive optics correction continues providing cutting-edge capabilities for studying the most extreme environments accessible to human observation. The adaptive optics revolution exemplifies how sustained technological development can eventually overcome obstacles that initially seem impossible to solve. From atmospheric distortion that once limited all ground-based astronomy to real-time correction systems achieving near-perfect image quality, this transformation illustrates the power of human ingenuity applied to fundamental scientific challenges. The transformation brought by adaptive optics technology cannot be overstated. It fundamentally revolutionized how astronomers study Sagittarius A star by converting fuzzy, distorted images into sharp, precise observations that revealed the true nature of our galactic center's crowded stellar environment. Stars that previously appeared as indistinct blobs suddenly emerged as crisp point sources, allowing researchers to track individual stellar motions with unprecedented accuracy. The central star cluster's complex structure became visible in extraordinary detail, revealing orbital patterns and stellar interactions that had remained hidden behind atmospheric turbulence for decades. This clarity enhancement proved essential for spectroscopic analysis, enabling astronomers to split starlight into component wavelengths with much greater precision. These detailed spectral measurements revealed crucial information about stellar velocities, chemical compositions, and how extreme gravitational environments affect stellar property. malts data that would have been impossible to obtain through distorted observations. The difference between pre- and post-adaptive optics capabilities resembled upgrading from severely blurred vision to perfect clarity. However, even with this revolutionary technology, observing the galactic center remained challenging due to persistent dust cloud interference that blocks most visible light wavelengths. The solution required combining adaptive optics with infrared observation capabilities, since longer wavelengths can penetrate dust clouds that completely obscure visible light. This powerful combination, real-time atmospheric correction paired with infrared sensitivity, unlocked many of the most significant discoveries about Sagittarius A star's properties and behavior. Critical measurements like gravitational redshift detection in light from star C, precise orbital mapping for mass calculations, and identification of brief flares would have remained impossible without adaptive optics enhancement. The technology enabled ground-based telescopes to compete directly with space-based facilities while maintaining advantages in aperture size and upgrade flexibility. Modern adaptive optics systems represent marvels of engineering precision, employing deformable mirrors made from specialized materials like thin glass or metal coated with reflective surfaces. Hundreds of tiny actuators push and pull different mirror regions to create optimal shapes that counteract atmospheric distortion in real time. The precision requirements are staggering. Mirror adjustments often measure smaller than human hair widths, yet produce profound improvements in image clarity. Early systems provided general distortion correction, but struggled with fine-scale details, while contemporary installations can address different atmospheric layers independently. Multi-conjugate adaptive optics systems use multiple reference points and several deformable mirrors to correct atmospheric turbulence at various altitudes separately. Lower atmosphere wind patterns, high-altitude jet streams, and ground-level heat effects all contribute different distortion components that require individual compensation. This multi-layer correction approach enables wider field imaging with more uniform quality across larger sky areas, particularly valuable for studying the extended region around Sagittarius A star. Astronomers can now detect subtle brightness variations, positional shifts, and other phenomena that might indicate unseen companions, gas clouds, or hotspot motions near the event horizon. The groundbreaking 2019 image of M87's supermassive black hole represented humanity's first direct visual confirmation of these theoretical objects, while paving the technological pathway toward imaging our own galactic monster. This achievement required overcoming seemingly impossible technical challenges through unprecedented international collaboration and innovative data processing techniques. M87's black hole, containing approximately 6.5 billion solar masses, presented several advantages that made it the logical first target for Event Horizon Telescope observations. Its enormous mass creates a correspondingly large event horizon shadow that appears more prominently against the surrounding luminous material, despite the object's location in a galaxy 55 million light-years away. The substantial mass also means orbital motions near the event horizon occur more slowly compared to smaller black holes like Sagittarius A star. Material takes hours or days to complete orbits rather than minutes, providing stable emission patterns that remain consistent throughout observation campaigns lasting several days. No single telescope on Earth possesses sufficient resolution to directly image black hole event horizons. Achieving the necessary angular resolution requires a telescope approximately Earth-sized, an obviously impossible engineering challenge for any conventional instrument design. The solution involved transforming our entire planet into a single enormous telescope through very long baseline interferometry techniques. The coordination requirements pushed technological precision to extraordinary limits. Atomic clocks synchronized participating observatories with accuracy levels that would lose less than 1 second over millions of years. Each facility collected massive data volumes that couldn't be transmitted electronically due to bandwidth limitations, requiring physical transportation of specialized hard drives to central processing facilities. The April 2017 observation campaign demanded perfect weather conditions at every participating site, since poor atmospheric conditions at even one telescope could compromise the entire dataset. Multiple nights of coordinated observations at 1.3 mm wavelengths captured radio emissions from superheated matter spiraling toward the event horizon. Data processing represented an equally formidable challenge requiring months of intensive computational work. Petabytes of raw information needed correlation and calibration to match timestamps perfectly, while reconstructing interference patterns from signals recorded across global telescope networks. Image reconstruction algorithms had to compensate for incomplete coverage inherent in Earth-based telescope distributions, filling data gaps through sophisticated mathematical techniques. To avoid bias, multiple independent teams processed the same data without knowledge of other groups' results, ultimately producing remarkably consistent images. The April 10th, 2019 revelation stunned the scientific community and captured global public imagination. The distinctive orange ring surrounding a dark central shadow provided visual confirmation of general relativity predictions in the universe's most extreme gravitational environments. The shadow's size and shape matched theoretical calculations almost perfectly, validating decades of black hole research, while demonstrating that millimeter wavelength interferometry could indeed image these exotic objects. The bright emission ring originated from synchrotron radiation produced by electrons spiraling along magnetic field lines at relativistic speeds. Asymmetric brightness patterns around the ring revealed matter moving at near-light velocities, with one side appearing brighter due to relativistic beaming effects that boost emission from material approaching Earth. These observations provided unprecedented insights into black hole accretion physics and magnetic field behavior. The M87 image's success validated theoretical models while opening pathways toward even more ambitious projects. Scientists gained confidence in their computational techniques and observational strategies, while refining algorithms needed for more challenging targets like Sagittarius A star. Despite being thousands of times closer than M87's black hole, imaging Sagittarius A star presented exponentially greater technical challenges that pushed Event Horizon Telescope capabilities to their absolute limits. Our galactic center's proximity advantage was completely overwhelmed by its dynamic, rapidly changing nature and compact apparent size. From Earth's perspective, Sagittarius A star appears roughly equivalent to observing a donut placed on the lunar surface, just an extraordinarily tiny angular size that demands maximum resolution capabilities from ground-based interferometry networks. The 4 million solar mass black hole creates a much smaller shadow than M87's giant, requiring more sensitive detection techniques and longer observation campaigns. Most significantly, Sagittarius A star displays highly dynamic behavior, with emission patterns changing on timescales of minutes rather than the hours or days characterizing M87's more stable environment. Superheated plasma whirls around our black hole at tremendous speeds, causing brightness and structural variations that blur traditional imaging approaches designed for static targets. This variability meant that conventional data processing techniques developed for M87 observations required fundamental modification to handle rapidly evolving source structure. Scientists needed to develop new algorithms capable of identifying persistent features while filtering out transient variations that would otherwise create image artifacts. The imaging challenge was further complicated by Sagittarius A star's location behind dense dust clouds that absorb and scatter electromagnetic radiation across many wavelengths. While millimeter wave observations can penetrate much of this obscuring material, some signal degradation inevitably occurs during the 26,000 light-year journey from galactic center to Earth. Despite these formidable obstacles, the eventual success in imaging Sagittarius A star validated theoretical predictions, while providing our first direct visual evidence of the monster lurking at our galaxy's heart. The achievement demonstrated that even the most challenging astronomical targets can yield to sustained technological development and innovative analysis techniques. The fundamental challenge in imaging Sagittarius A star stems from its hyperactive nature, where superheated plasma whirls around the event horizon at such tremendous velocities that complete orbital cycles occur within mere minutes. This creates a constantly shifting kaleidoscope of emission patterns that change faster than traditional astronomical imaging techniques can accommodate. Unlike M87's relatively sedate black hole, where structural features remain stable for days or weeks, our galactic monster transforms its appearance on timescales comparable to human attention spans. Material orbiting just outside the event horizon reaches significant fractions of light speed, creating relativistic effects that cause brightness patterns to dance and morph continuously. This rapid variability transforms the imaging process from conventional astronomical photography into something resembling an attempt to capture a sharp portrait of flickering candle flames during a windstorm. Long exposure techniques that work perfectly for stable targets become counterproductive when the subject undergoes fundamental structural changes during observation periods. The challenge intensifies due to Sagittarius A star's location deep within our galaxy's dusty central regions. While M87's radio waves traverse mostly empty intergalactic space before reaching Earth, signals from our galactic center must penetrate thousands of light years of intervening material that scatters and distorts the emissions we're trying to detect. Dust particles throughout the galactic plane act like cosmic fog, blurring fine details while adding noise to the already challenging observations. Even sophisticated data processing techniques cannot fully compensate for this interference, meaning some structural information inevitably disappears during the 26,000 light-year journey from source to detector. Synchronization requirements for Sagittarius A star observations pushed international coordination to unprecedented levels of precision. Every participating telescope across the global network needed to capture identical moments of the rapidly evolving target, requiring timing accuracy measured in fractions of seconds across multiple continents. Weather constraints became exponentially more critical compared to M87 observations. The Event Horizon Telescope network spans from Chilean mountaintops to Hawaiian peaks to Antarctic research stations, and clear skies were simultaneously required at every location during brief observing windows when the black hole occupied optimal positions in Earth's sky. A single storm system or cloud formation at any participating site could compromise the entire observational campaign, creating logistical challenges comparable to orchestrating a global symphony where every musician must play identical notes at precisely the same instant, despite being separated by thousands of miles. The historic 2022 image of Sagittarius A star represented a monumental achievement in observational astronomy, yet it simultaneously revealed the vast frontiers of knowledge that remain unexplored about our galactic center's true nature. The photograph answered some fundamental questions while raising dozens of new mysteries that will drive research for decades to come. Perhaps the most significant limitation involves determining Sagittarius A star's rotation rate, a crucial parameter that influences everything from matter in fall patterns to jet formation mechanisms. Black holes can spin anywhere from zero rotation to the theoretical maximum allowed by general relativity, and this angular momentum profoundly affects the surrounding space-time geometry. The rapid variability that made imaging so challenging also obscures rotational signatures that might be detectable in more stable systems. While M87's black hole maintains consistent structural features long enough for spin analysis, Sagittarius A star's constantly shifting emission patterns prevent similar measurements using current techniques. The average nature of the final image compounds this problem. To achieve sufficient signal quality, researchers had to combine observations across multiple time periods, smoothing out temporal variations that might otherwise reveal rotational characteristics. The spin information may still be encoded within the raw data, awaiting development of more sophisticated analysis methods. Equally mysterious is the black hole's three-dimensional orientation relative to Earth. While planets have obvious poles and equators, black holes possess rotational axes that can point in any direction through space. Understanding this orientation proves crucial for interpreting matter flow patterns, energy release mechanisms, and interactions with the broader galactic environment. M87's prominent jet provides a clear directional reference that simplifies orientation analysis, but Sagittarius A star lacks such obvious guideposts. Any outflows from our galactic center remain too weak for easy detection through the crowded, dust-obscured central regions of the Milky Way. Magnetic field architecture represents another major unknown despite its fundamental importance for black hole physics. These invisible structures guide matter flows, trigger explosive reconnection events, and potentially regulate feeding rates through mechanisms we're only beginning to understand. The initial Event Horizon Telescope observations focused primarily on total intensity measurements, rather than the polarized light signatures that reveal magnetic field orientations and strengths. Follow-up polarization studies are beginning to address this gap, but comprehensive magnetic field mapping remains years away. The time-averaged nature of the published image masks the dynamic processes occurring on minute-to-minute timescales that could provide crucial insights into matter behavior near the event horizon. Real-time movies showing hotspot motions, flare developments, and structural evolution would offer unprecedented windows into extreme gravity physics. Current technology requires hours or days of data accumulation to achieve sufficient image quality, preventing the rapid-fire observations needed for dynamic studies. Future improvements in sensitivity and resolution may eventually enable the cosmic cinematography that would truly revolutionize black hole understanding. Mass accretion rates, the amount of material actually crossing the event horizon, remain poorly constrained despite their fundamental importance for understanding black hole growth and energy output. The faint emission we observe could result from extremely low feeding rates, or from highly inefficient radiative processes that convert most gravitational energy into forms we cannot easily detect. Even the shadow size measurements, while consistent with general relativity predictions, retain sufficient uncertainty to leave room for alternative gravity theories. More precise imaging could tighten these constraints, potentially providing definitive tests of Einstein's equations in the strongest gravitational fields accessible to human observation. Beyond the event horizon lies a realm that challenges our fundamental understanding of physics, causality, and the nature of reality itself. Classical general relativity paints a stark picture of this forbidden zone MON, a region where all trajectories lead inexorably toward the central singularity, with no possibility of orbital motion or escape. According to Einstein's equations, space-time curvature within the event horizon becomes so extreme that the normal distinction between space and time dimensions breaks down. What we perceive as spatial directions in the external universe transform into temporal coordinates inside the black hole, making conventional concepts of position and movement meaningless. The journey toward the singularity appears inevitable and brief from the perspective of infalling matter. Tidal forces grow stronger with each passing moment, stretching objects along the radial direction while compressing them perpendicular to their fall. This spaghettification effect would ultimately tear apart any material structure long before reaching the mathematical point of infinite density at the center. Yet modern physics suggests this classical picture may be incomplete or entirely wrong. Quantum mechanics introduces uncertainty principles and virtual particle effects that could fundamentally alter conditions near the singularity. Some theories propose that quantum pressure might halt gravitational collapse before infinite density is reached, creating exotic objects like Planck stars with finite but incredibly high densities. Other speculative models suggest black hole interiors might connect to distant regions of spacetime through Einstein-Rosen bridges or wormholes, though the stability and traversability of such structures remain highly questionable. Alternative theories propose that black holes might be fuzzballs, minus extended quantum objects without true event horizons or interior regions. The fundamental problem with all interior speculation is the absolute impossibility of obtaining observational evidence. No information can ever escape from beyond the event horizon to confirm or refute any theoretical model, making black hole interiors perhaps the most purely theoretical realm in all of physics. This informational barrier creates unique challenges for scientific methodology, which traditionally relies on experimental verification of theoretical predictions. Black hole interiors represent the ultimate limit case, where theory must operate without any possibility of direct empirical confirmation. Nevertheless, the interior structure question remains scientifically important, because it connects to fundamental issues about quantum gravity, the nature of space-time, and the ultimate fate of information that falls into black holes. These deep theoretical questions may eventually find resolution through indirect approaches or breakthrough insights that don't require direct interior observation. For now, the region inside Sagittarius A star's event horizon remains forever hidden behind the most impenetrable barrier in the known universe, leaving physicists to wonder whether conventional spacetime even exists in that realm, or whether entirely new physics governs the ultimate gravitational extreme. The frontiers of theoretical physics push even further into uncharted territory, with concepts that challenge our most basic assumptions about reality itself. String theory contributions to black hole understanding propose fuzzballs, minus exotic objects composed entirely of tangled strings of fundamental energy rather than conventional matter or empty space. In this radical framework, black holes wouldn't contain interior voids or central singularities, but instead consist of incredibly complex knots of vibrating strings that create all observed gravitational and electromagnetic effects from their collective behavior. From external vantage points, these fuzzball structures would appear indistinguishable from conventional black holes while avoiding the mathematical infinities that plague classical theories. Even more speculative proposals suggest black holes might serve as mouths of wormholes, cosmic tunnels connecting distant regions of space-time or entirely separate universes. If Sagittarius A star represented such a gateway, our galactic center would function as a cosmic portal to realms beyond current scientific imagination. These ideas remain almost entirely theoretical, existing primarily in mathematical frameworks rather than observational evidence. However, they persist in scientific discourse because black holes continue generating fundamental questions that conventional physics struggles to answer completely. The central challenge facing all alternative theories is that Sagittarius A star behaves exactly like a black hole should according to general relativity predictions. Every observation, from stellar orbital mechanics to event horizon telescope imaging, remains consistent with standard black hole models without requiring exotic alternatives. Yet scientific methodology demands continued questioning and exploration of seemingly unlikely possibilities. Each new observation brings us incrementally closer to understanding the true nature of our galactic center, though definitive answers may remain elusive for generations. The fundamental question persists. Are we truly certain about what lurks at the Milky Way's heart, or have we barely begun scratching the surface of cosmic reality's deepest mysteries? Sagittarius A star's influence on Milky Way evolution extends far beyond its current quiet state, representing a cosmic architect whose construction project has spanned over 13 billion years of galactic development. Understanding this relationship requires examining how supermassive black holes and their host galaxies co-evolve through intimate gravitational partnerships that shape cosmic structure across vast timescales. During the Milky Way's tumultuous youth, our galaxy bore no resemblance to today's elegant spiral structure. Instead, chaotic collections of gas clouds, dust, and merging proto-galaxies created a cosmic construction zone where modern galactic components were slowly assembling through gravitational interactions. Sagittarius A star likely began as a much smaller black hole seed, perhaps the remnant of one of the universe's first massive stars or a direct collapse object formed from primordial gas clouds. As surrounding matter gradually accumulated through gravitational attraction, the growing black hole created an increasingly deep gravitational well that influenced how material collected in the central regions. Computer simulations of early galactic evolution suggest central black holes play crucial roles in organizing surrounding matter distributions. Their gravitational influence can funnel gas inward, accelerating bulge formation while simultaneously preventing runaway star formation that might consume available material too rapidly. However, the relationship between black holes and galactic development involves complex feedback mechanisms that can operate in opposite directions depending on activity levels. During quiet phases, Sagittarius A star's gravity would primarily organize matter flows without dramatically altering star formation rates, but active feeding periods could generate powerful outflows that sweep gas from central regions, temporarily halting stellar birth processes. The balance between these competing effects, matter accumulation versus energy-driven dispersal, likely determined many characteristics of the Milky Way's current structure. Modern observations reveal tight correlations between central black hole masses and galactic bulge properties across diverse galaxy populations, suggesting these relationships reflect fundamental co-evolutionary processes rather than mere coincidence. Evidence for past activity periods comes from several sources, including the enigmatic Fermi bubbles extending 25,000 light-years above and below our galactic plane. These enormous gamma-ray structures likely originated from explosive episodes when Sagittarius A star operated as a miniature quasar, demonstrating that our currently quiet black hole once wielded sufficient energy to affect the entire galactic environment. Such active phases could have prevented rapid star formation in inner galactic regions, allowing spiral arm structures to develop over extended timescales rather than being disrupted by early stellar overcrowding. The regulated star formation enabled by black hole feedback might explain why the Milky Way achieved its current balanced structure rather than evolving into a more chaotic configuration. Sagittarius A star's gravitational influence extends through the galactic bar Milos, the elongated stellar structure, crossing our galaxy's center that channels material inward from spiral arms. This bar system may depend partially on central mass concentration for stability, with the black hole helping maintain organized matter flows that feed both ongoing star formation and occasional black hole growth episodes. Chemical evolution throughout the Milky Way also bears potential signatures of central black hole influence. By controlling where and when star formation occurred, Sagittarius A star could have indirectly affected how heavy elements produced in stellar cores were distributed throughout the galaxy. Regions where black hole activity cleared gas would experience delayed star formation, affecting the timing of element recycling into subsequent stellar generations. However, the black hole's influence has clear limitations determined by distance and competing gravitational forces. The Milky Way's outer regions, where our solar system resides, remain largely unaffected by central black hole dynamics. Spiral arm structures in these distant zones result primarily from density waves propagating through the galactic disk rather than processes originating at the core. This distance limitation means Sagittarius A star likely influenced inner galactic structure and bulge formation while playing minimal roles in outer disk evolution. The galaxy's sweeping spiral arms developed through mechanisms largely independent of central black hole activity, though indirect effects through chemical evolution or early structural organization cannot be completely ruled out. Revolutionary advances in astronomical instrumentation promise to transform our understanding of Sagittarius A star, while pushing black hole research into unprecedented territory. Current Event Horizon telescope capabilities represent merely the beginning of a technological evolution that will eventually enable real-time movies of matter spiraling toward our galactic monster's event horizon. The most immediate improvements involve expanding the global telescope network through strategic placement of additional radio dishes in currently underrepresented regions. Africa represents a particularly valuable target for new installations, as Southern Hemisphere coverage would significantly enhance imaging capabilities while filling critical gaps in the virtual Earth-sized telescope array. Pacific Ocean installations present unique opportunities for mobile or floating observatory platforms that could access optimal observing positions impossible with fixed land-based facilities. Ship-mounted telescopes or purpose-built floating platforms could reach coordinates that provide ideal geometric configurations for specific observation campaigns. Each additional telescope location increases the effective resolution of the combined array while providing redundancy against equipment failures or weather disruptions that currently threaten entire observing campaigns. More telescope sites also enable simultaneous observations at multiple wavelengths, revealing different physical processes operating around black holes. Space-based radio telescopes represent the ultimate frontier for black hole imaging technology. Orbital platforms would escape atmospheric limitations entirely, while enabling baseline distances far exceeding Earth's diameter. Such space-based arrays could achieve angular resolution capabilities that dwarf current ground-based networks. Several proposed missions envision coordinated space telescopes operating at Lagrange points or in independent solar orbits, creating interferometric arrays spanning millions of kilometers. These extended baselines would provide resolution sufficient for detailed studies of matter flows just outside event horizons, while potentially enabling observations of black hole rotation signatures. Advanced data processing algorithms continue improving our ability to extract information from existing observations, while preparing for future campaigns generating unprecedented data volumes. Machine learning techniques now contribute to image reconstruction processes, identifying subtle patterns that traditional analysis methods might miss. Real-time observation capabilities represent perhaps the most exciting near-term development. Rather than averaging observations over days or weeks to achieve sufficient signal quality, future systems may enable minute-by-minute monitoring of dynamic processes around Sagittarius A star. Such temporal resolution would reveal hotspot motions, flare development, and structural evolution in the immediate vicinity of the event horizon. These observations could provide direct tests of general relativity predictions about matter behavior in extreme gravitational fields, while revealing the detailed physics governing black hole feeding processes. Multi-wavelength coordination between different types of observatories will create comprehensive pictures of black hole environments across the entire electromagnetic spectrum. Radio telescopes reveal emission from cold gas, infrared observations penetrate dust clouds, X-ray satellites detect hot plasma, and gamma-ray detectors identify the most energetic processes. Coordinated campaigns, combining all these capabilities with gravitational wave detectors, could potentially observe black hole mergers or other catastrophic events from multiple perspectives, simultaneously, providing unprecedented insights into extreme gravity physics. The technological development cycle continues accelerating as advances in computing power, detector sensitivity, and precision instrumentation enable observations that seemed impossible just decades ago. Each generation of improvements reveals new phenomena while raising fresh questions that demand even more sophisticated observational capabilities. Future discoveries around Sagittarius A star will likely transform our understanding not only of black holes but of fundamental physics operating under the most extreme conditions accessible to human investigation. The cosmic monster at our galaxy's heart continues serving as the ultimate laboratory for testing theoretical predictions about gravity, space-time, and the nature of reality itself. The journey from Carl Jansky's accidental radio detection to direct event horizon imaging demonstrates how sustained technological development can eventually overcome seemingly insurmountable observational challenges. Tomorrow's instruments will undoubtedly reveal cosmic secrets that remain completely hidden, using current capabilities, continuing humanity's greatest adventure in understanding our place within the universe's most extreme environments. Space-based radio interferometry represents the next quantum leap in black hole observation capabilities, promising to transform static images into dynamic movies that capture the real-time drama unfolding around Sagittarius A star's event horizon. These orbital platforms could extend baseline distances far beyond Earth's diameter, creating virtual telescopes of unprecedented size and resolution. Future space-based arrays might position radio telescopes at strategic locations throughout the solar system, enabling interferometric baselines spanning millions of kilometers. Such configurations would achieve angular resolution capabilities that make current Earth-based networks appear primitive by comparison, potentially revealing structural details on scales approaching the event horizon itself. The technological challenges of space-based very long baseline interferometry have been partially tested through previous missions, but applying these techniques to black hole imaging demands precision and stability beyond anything previously attempted. Orbital platforms must maintain exact positioning while synchronizing observations across vast distances with timing accuracy measured in nanoseconds. Data handling represents another revolutionary frontier, where current limitations will soon disappear entirely. The Event Horizon Telescope generates massive data volumes that currently require physical transportation of storage devices between facilities, but future systems will employ ultra-high-speed connections, enabling real-time data streaming between global telescope sites. This connectivity revolution will allow astronomers to process interferometric signals immediately, rather than waiting months for results, enabling rapid response to transient events like the mysterious flares that periodically illuminate our galactic center. Near real-time processing could reveal dynamic phenomena that remain invisible using current time-averaged analysis techniques. Artificial intelligence algorithms increasingly contribute to data processing workflows, recognizing subtle patterns in interferometric measurements that traditional software might miss entirely. Machine learning systems can identify optimal image reconstruction parameters while automatically flagging unusual activity for immediate follow-up observations. Multi-wavelength observations will add entirely new dimensions to black hole studies by simultaneously capturing emissions across multiple radio frequencies. While current Event Horizon Telescope observations operate at a single 1.3 mm wavelength chosen for optimal atmospheric transmission, future campaigns will employ multiple bands simultaneously. Shorter wavelengths like 0.87 mm would provide enhanced resolution but require extremely sophisticated equipment to handle the correspondingly fragile signals. Longer wavelengths could reveal cooler gas at greater distances from the event horizon, providing comprehensive pictures of the entire accretion environment rather than just the innermost regions. These multi-band observations will create the equivalent of color images for black holes, though the colors represent different physical processes rather than visible hues. Temperature variations, velocity fields, and magnetic structures would become distinguishable through their distinctive spectral signatures. Extended observation campaigns represent another crucial advancement that could transform our understanding of black hole variability. Current imaging requires perfect weather simultaneously at all participating telescopes worldwide, limiting observations to brief windows when conditions align favorably across multiple continents. Advanced weather prediction and flexible scheduling protocols will enable longer observation periods that capture temporal evolution in the black hole environment. Rather than static snapshots averaged over days, future campaigns might track structural changes hour by hour, revealing the dynamic processes that current techniques can only glimpse indirectly. The ultimate goal involves creating time-lapse movies showing matter spiraling towards Sagittarius A star, while hotspots orbit just outside the event horizon. Such cosmic cinematography would provide unprecedented tests of general relativity predictions about matter behavior in extreme gravitational fields. Integration with other major telescope projects will multiply the scientific return from black hole observations. The square-kilometre array, currently under construction in Australia and South Africa, will become the world's largest radio telescope through thousands of coordinated antenna elements spanning enormous areas. While not specifically designed for Event Horizon Telescope-style interferometry, the square-kilometre array could contribute sensitivity enhancements that enable detection of fainter emission features around Sagittarius A star. Thin plasma streams, weak outflows, or subtle structural variations might become observable through such enhanced capabilities. Lunar-based observatories represent perhaps the most ambitious long-term vision for black hole research. The Moon's lack of atmosphere would eliminate the distortions that limit ground-based observations while enabling continuous operations uninterrupted by Earth's day-night cycle. Lunar telescope stations operating in coordination with Earth-based facilities would create interferometric baselines of extraordinary extent, pushing resolution capabilities toward theoretical limits. The engineering challenges of lunar construction and maintenance remain formidable, but the scientific potential could justify such investments for next-generation black hole studies. X-ray polarimetry represents one of the most promising techniques for unraveling Sagittarius A star's rotational mysteries, while providing insights into the fundamental physics governing matter behavior in extreme gravitational environments. Understanding black hole spin rates could reveal crucial information about formation mechanisms, growth histories, and energy storage capabilities. The rotational velocity of supermassive black holes encodes their evolutionary stories like cosmic fingerprints. Rapid rotation typically indicates steady accretion from aligned matter sources such as galactic disks, while slow or chaotically oriented spins suggest violent merger histories involving black holes approaching from random directions. Amend detection requires sophisticated indirect methods since rotation cannot be observed directly. The most promising approach involves analyzing polarization patterns in X-ray emissions generated by superheated matter spiraling toward the event horizon under the combined influences of extreme gravity and intense magnetic fields. Light consists of electromagnetic waves that can vibrate in multiple orientations, but specific physical processes can align these vibrations into particular patterns. When X-rays from the black hole environment reach Earth with distinctive polarization signatures, they carry encoded information about the conditions that shaped their properties during emission and propagation. Frame dragging represents the key physical phenomenon that connects black hole spin to observable polarization effects. Rapidly rotating black holes literally drag surrounding space-time along with their rotation, creating asymmetric gravitational fields that influence photon trajectories in measurable ways. X-rays generated near the event horizon experience complex scattering processes as they navigate through the warped space-time geometry surrounding spinning black holes. The resulting polarization patterns depend sensitively on rotation rates, enabling astronomers to work backward from observed signatures to infer spin parameters. However, X-ray polarimetry demands extraordinary instrumental sophistication that has only recently become technologically feasible. Unlike conventional X-ray astronomy that measures photon energies and arrival times, polarimetry requires determining the three-dimensional orientation of each photon's electric field vector. This measurement challenge is compounded by Earth's atmospheric absorption of cosmic X-rays, necessitating space-based observations using satellites or high-altitude balloon platforms. The instrumental requirements include ultra-stable detector systems capable of maintaining calibration across the extreme temperature and radiation environments of space. NASA's Imaging X-ray Polarimetry Explorer, launched in December 2021, represents the first dedicated mission optimized for cosmic X-ray polarimetry. This specialized observatory carries instruments specifically designed to measure polarization signatures from various celestial sources, including pulsars, supernova remnants, and active galactic nuclei. Sagittarius A star presents unique observational challenges for X-ray polarimetry due to its relatively faint emission compared to more active supermassive black holes in distant galaxies. Current technology requires the enhanced X-ray brightness during flare episodes to achieve sufficient signal-to-noise ratios for meaningful polarization measurements. Future polarimetry missions will feature larger collecting areas for gathering more X-ray photons, improved detector resolution for separating black hole emissions from the crowded galactic center background, and enhanced timing capabilities for tracking polarization changes during brief flare events. These technological advances could enable real-time monitoring of polarization angle variations as matter completes orbital cycles near the event horizon. Such observations would provide direct measurements of both spin magnitude and rotational axis orientation relative to our line of sight. Fast-spinning black holes store tremendous rotational energy that can power jets, winds, and other energetic phenomena through magnetic field interactions. Even though Sagittarius A star currently lacks prominent jets, its spin rate might still influence gas dynamics and magnetic field configurations in the immediate environment. Spin measurements also serve as fossil records of past evolutionary episodes. High spin rates aligned with the galactic plane would suggest steady growth through disk accretion, while low or randomly oriented spins might indicate chaotic merger histories involving black holes from various directions. The dynamic nature of spin presents another fascinating research frontier. If Sagittarius A star enters more active feeding phases, newly accreted matter could either increase or decrease rotational velocity depending on its angular momentum orientation relative to the existing spin direction. Long-term polarimetry monitoring could track these spin evolution processes over years or decades, transforming spin from a static parameter into a dynamic quantity that changes in response to environmental conditions and feeding episodes. Spin measurements provide crucial tests of general relativity in the strongest gravitational fields accessible to human observation. Einstein's equations make specific predictions about how rotating black holes warp space-time and influence light polarization, and any deviations from these predictions could indicate new physics beyond current theoretical frameworks. Polarimetry also offers methods for disentangling gravitational effects from magnetic field influences in the complex environment surrounding black holes. Both phenomena can polarize light through different mechanisms, and comparing polarization signatures across multiple X-ray energies helps separate these competing contributions. Advanced interferometric X-ray polarimetry concepts envision polarization mapping at extremely fine angular resolution, potentially identifying specific regions within the accretion flow that contribute most strongly to observed signals. For Sagittarius A star, such capabilities might locate the precise origins of flare emissions within the immediate vicinity of the event horizon. The long-term vision involves making polarimetry as routine as current brightness or spectral measurements, enabling systematic surveys of black hole populations to understand the relationships between spin, mass, environment, and activity levels across diverse cosmic settings. As polarimetry technology matures, it will become an indispensable tool for studying the most extreme gravitational environments in the universe, while providing fundamental tests of our understanding about space-time, matter, and energy under conditions that push physical theories to their absolute limits. The rotational secrets locked within Sagittarius A star await revelation through these sophisticated new techniques, promising to transform our understanding of how supermassive black holes form, evolve, and interact with their galactic environments across cosmic history. X-ray polarimetry currently occupies the frontier of astronomical instrumentation, representing a revolutionary technique that could unlock entirely new dimensions in black hole research. For Sagittarius A star specifically, this approach offers an unprecedented method for investigating the hidden evolutionary history encoded within its rotational characteristics. While we cannot dispatch physical probes beyond the event horizon to directly examine black hole interiors, polarimetry enables us to decode the cosmic stories written in the subtle twisting patterns of spacetime itself. Each X-ray photon carries encoded information about the extreme conditions it encountered during emission and propagation through the warped geometry surrounding our galactic monster. The polarization signatures preserve detailed records of magnetic field configurations, matter flow dynamics, and gravitational effects that would otherwise remain completely inaccessible to conventional observational techniques. These cosmic messengers travel across 26,000 light-years of space, while maintaining their orientation information, delivering data about the most extreme physical conditions accessible to human investigation. Gravitational wave astronomy opens entirely new sensory channels for studying Sagittarius A star, though detecting such signals requires extraordinary cosmic events to generate measurable distortions in space-time fabric. A stable, isolated black hole like our galactic center produces gravitational fields without the dynamic changes necessary for wave generation detectable by current technology. Gravitational waves emerge only from accelerating masses that create time-varying distortions in space-time geometry. For Sagittarius A star, this means dramatic events like smaller black holes spiraling inward, massive stars being tidally disrupted, or collision events within the immediate galactic center environment. The most promising scenario involves extreme mass ratio, in spirals events where stellar mass objects become gravitationally captured by Sagittarius A star and slowly spiral toward destruction over thousands or millions of years. As these doomed objects approach ever closer to the event horizon, they accelerate to tremendous velocities while generating increasingly intense gravitational wave signatures. These death spiral events would produce low-frequency gravitational waves completely beyond the detection capabilities of ground-based instruments like LIGO or Virgo, which are optimized for higher frequency signals from stellar mass black hole, mergers occurring in milliseconds rather than millennia. Future space-based gravitational wave observatories, like the planned laser interferometer, space antenna represent the key to unlocking this cosmic symphony. LISA employs 3 spacecraft positioned millions of kilometers apart and connected by precisely controlled laser beams to detect the minute space-time distortions caused by massive objects in slow orbital decay. This enormous baseline sensitivity enables detection of millihertz gravitational waves, exactly the frequency range expected from objects spiraling into supermassive black holes over extended timescales. If a stellar mass black hole or neutron star ever becomes trapped in a death spiral towards Sagittarius A star, LISA could theoretically detect the process years before the final plunge occurs. Such advance warning would provide unprecedented opportunities for coordinated multi-messenger astronomy campaigns, with telescopes across the electromagnetic spectrum preparing to observe the ultimate cosmic collision from radio wavelengths through X-rays and gamma rays simultaneously. More exotic gravitational wave sources near the galactic center could include sudden stellar core collapses, forming new black holes, neutron star disruptions under extreme tidal forces, or other catastrophic events producing brief but incredibly violent space-time disturbances detectable by current ground-based facilities. However, such events remain extremely rare and unpredictable, requiring extraordinary timing coincidence for detection during active observation periods. The scientific community would need remarkable fortune for such phenomena to occur close enough to Sagittarius A star during operational phases of existing gravitational wave detectors. Successful gravitational wave detection from the galactic center would provide scientific benefits far exceeding anything possible through electromagnetic observations alone. Mass and spin measurements could achieve precision levels impossible using light-based techniques, while providing direct tests of general relativity in the strongest gravitational fields accessible to human investigation. Unlike electromagnetic radiation that can be scattered, absorbed, or distorted by intervening matter, gravitational waves propagate through the universe, essentially unimpeded by gas clouds, dust, or magnetic fields. This transparency offers completely unfiltered views of processes occurring immediately outside the event horizon, regions forever hidden from direct electromagnetic observation. The technical requirements for gravitational wave detection from supermassive black holes demand extraordinary instrumental sensitivity, combined with years of continuous observation. Signals often remain buried within detector noise for months or years, requiring sophisticated data analysis techniques to extract meaningful information from seemingly random fluctuations. Coordination between gravitational wave detection and conventional telescope observations presents additional timing challenges, especially for events lasting extended periods. Projects like LISA face planned deployment in the 2030s or later, requiring extensive engineering development and testing before such delicate instruments can operate reliably in the space environment. Ground-based detector upgrades continue advancing sensitivity capabilities toward next-generation facilities like Cosmic Explorer in the United States and the Einstein Telescope in Europe. While these enhanced instruments cannot detect the slow in-spirals characteristic of supermassive black hole interactions, they could identify brief high-frequency bursts from sudden disruption events near the galactic center. Future networks of space-based gravitational wave observatories distributed throughout the solar system could enable triangulation techniques similar to very long baseline interferometry methods used in radio astronomy. Multiple detector platforms would pinpoint wave sources with extraordinary precision, while enabling real-time coordination with electromagnetic telescopes whenever unusual activity occurs. Approximately 4 billion years in the future, our galaxy faces its most dramatic transformation as the inevitable collision with Andromeda Galaxy reshapes both stellar systems into an entirely new cosmic structure. This titanic encounter will fundamentally alter Sagittarius A star's environment, while creating the most spectacular feeding opportunity in our black hole's entire history. The approaching merger unfolds at speeds that seem extraordinary by human standards, roughly 110 kilometers per second. This represents a glacially slow process on cosmic timescales. This gradual approach provides ample time for gravitational forces to begin distorting both galaxies long before direct interaction occurs. At the heart of this cosmic drama lie two supermassive black holes, our familiar Sagittarius A star, containing approximately 4 million solar masses, and Andromeda's central monster designated M31 star, with an estimated mass exceeding 100 million suns. These gravitational titans will ultimately determine the merger's most dramatic phases. Contrary to popular imagination, galactic collisions rarely involve direct stellar impacts due to the vast empty spaces separating individual stars. Instead, gravitational interactions create spectacular rearrangements of stellar orbits, gas clouds, and dust distributions, while triggering intense bursts of new star formation in compressed regions. The true spectacle emerges through dynamical friction, a process where each supermassive black hole experiences drag from surrounding stars and dark matter that gradually robs orbital momentum until both monsters spiral inexorably toward each other across millions of years. This extended approach phase will fundamentally transform Sagittarius A star from its current quiet state into a blazing active galactic nucleus as disrupted gas streams and stellar debris pour toward the galactic center. The influx of fresh material could trigger feeding episodes more violent than anything experienced during our black hole's entire previous history. Both central black holes will likely undergo simultaneous awakening as collision-driven turbulence delivers unprecedented fuel supplies to their immediate environments. If both objects become active simultaneously, any surviving worlds within the merging galaxies would witness two brilliant points dominating their night skies, each outshining entire stellar populations through intense radiation from superheated accretion processes. The Milky Way's elegant spiral structure cannot survive such violent reorganization. Gravitational tides will stretch and distort stellar distributions while completely disrupting the organized rotation patterns that maintain our galaxy's current appearance. The collision's aftermath will likely produce an elliptical galaxy with a more spherical stellar distribution, lacking the defined spiral arms characterizing both original systems. This transformation represents far more than cosmetic rearrangement. The merger will fundamentally alter stellar formation patterns, chemical evolution processes, and habitability zones throughout the combined system. Existing planetary systems may experience orbital disruptions, while newly compressed gas regions trigger massive stellar nurseries that could reshape the chemical composition of future generations. The final merger between Sagittarius A star and M31 star will create one of the most massive black holes in the local universe, potentially exceeding 100 million solar masses, while releasing tremendous energy through gravitational wave emission. This cataclysmic event will generate space-time distortions detectable across cosmological distances, announcing the birth of a new cosmic giant. However, the merger timeline extends across such vast periods that no currently existing life forms will witness the conclusion of this cosmic dance. Humanity's biological lineage will have evolved beyond recognition or vanished entirely before the first significant interactions begin affecting our solar system's local environment. The collision process itself spans hundreds of millions of years, from initial gravitational influence through final black hole merger, ensuring that multiple complete cycles of stellar evolution occur during the transformation. Stars will be born, live complete lives, and die as stellar remnants, while the galactic merger progresses through its various phases. Solar system disruption remains highly unlikely, despite the galaxy-scale chaos surrounding the merger process. The probability of direct stellar encounters affecting our Sun remains negligible, even during the most violent interaction phases, though our solar system may be relocated to entirely different regions within the merged galaxy structure. The merged galaxy, tentatively named Milky Way by astronomers, will eventually settle into a stable configuration after the initial collision chaos subsides. This new system will possess different characteristics than either original galaxy, while hosting the combined stellar populations and chemical enrichment from both parent structures. The Andromeda collision represents just one example of the ongoing cosmic evolution that continuously reshapes galactic structures throughout the universe. Such merger events have occurred countless times throughout cosmic history, creating the diverse galaxy populations observed in modern astronomical surveys. For Sagittarius A star, the approaching collision promises to write the most dramatic chapter in its long evolutionary story, transforming our currently quiet galactic center into a brilliant beacon visible across cosmological distances, while creating a new supermassive black hole that will anchor galactic structure for billions of years into the far future. This cosmic collision course reminds us that even the most stable appearing cosmic structures remain subject to continuous evolution driven by gravitational forces, operating across timescales that dwarf human experience, while ultimately determining the fate of every object within our cosmic neighborhood. The gravitational choreography preceding the ultimate black hole merger will unfold over tens of millions of years as two supermassive monsters perform an increasingly frantic orbital ballet. Sagittarius A star and M31 star will circle each other at ever-decreasing distances, while radiating tremendous energy through gravitational waves that ripple across the fabric of space-time itself. These gravitational emissions, detectable by instruments far more advanced than current technology, will gradually rob the binary system of orbital energy, forcing the two black holes into tighter and more rapid spirals. The process accelerates exponentially as the event horizons approach, with orbital periods shrinking from millennia to centuries to mere years during the final phases. The climactic merger event will release more energy in gravitational waves than all the stars in both galaxies combined, produced through nuclear fusion across billions of years. This cataclysmic collision will create space-time distortions detectable across cosmological distances, announcing the birth of a new supermassive giant to civilizations throughout the observable universe. The resulting black hole could exceed 100 million solar masses, depending on how much additional matter falls inward during the violent merger process. Its rotational characteristics will preserve the entire evolutionary history of both parent galaxies, encoding information about ancient star formation episodes, past merger events, and the complex gravitational interactions that shaped billions of years of cosmic development. Meanwhile, the stellar populations of both galaxies will experience dramatic redistribution as gravitational chaos destroys the organized orbital patterns that previously maintained stable galactic structure. Stars that once followed neat, nearly circular paths around their respective galactic centers will be scattered into random trajectories, with some objects gaining sufficient velocity to escape into intergalactic space entirely. Planetary systems face particularly uncertain fates during this gravitational upheaval. Many worlds will likely be dislodged from their parent stars through close encounters with other stellar systems, creating vast populations of rogue planets wandering the darkness between galaxies. These lonely worlds, cut off from stellar warmth, would become frozen wastelands drifting through the cosmic void. The profound question of whether Earth will survive to witness this cosmic spectacle requires examining multiple existential threats operating across vastly different timescales. 4 billion years represents an almost incomprehensible duration, roughly equivalent to the entire span of time since life first emerged on our planet. Our sun's evolutionary timeline poses the most immediate long-term threat to terrestrial habitability. As a main sequence star, the sun gradually increases its luminosity over geological time through natural fusion processes that slowly alter its internal structure. Within 1 to 2 billion years, this enhanced energy output will trigger catastrophic climate changes that could render Earth uninhabitable. Rising solar luminosity will eventually cause atmospheric water vapor to reach critical concentrations that trigger runaway greenhouse effects. Similar to the conditions that transformed Venus into a hellish wasteland, Earth's oceans will begin evaporating into space, stripping away the water essential for all known life while leaving behind a desiccated, sterile world. Even if terrestrial life somehow survives these climatic challenges, the sun's continued evolution will ultimately seal Earth's fate. In approximately 5 billion years, our star will exhaust its core hydrogen fuel and expand into a red giant phase, potentially engulfing the inner planets entirely. The intense radiation and stellar wind from this bloated stellar phase would obliterate any remaining traces of Earth's biosphere. The galactic collision itself introduces additional uncertainties about our solar system's long-term stability. While direct stellar collisions remain statistically negligible due to the vast spaces between stars, gravitational interactions during galaxy merger events can dramatically alter stellar orbits across the combined system. Our solar system might be gravitationally ejected toward the merged galaxy's outer regions, where reduced stellar density would provide a quieter cosmic environment, but potentially expose Earth to higher cosmic ray fluxes due to decreased magnetic field shielding. Alternatively, we could be scattered inward toward the active galactic center, where intense radiation and gravitational disturbances would create extremely hazardous conditions for biological survival. The most catastrophic scenario involves close encounters with other stellar systems during the merger's chaotic phases. Even relatively distant passages by neighboring stars could perturb planetary orbits sufficiently to destabilize Earth's carefully balanced trajectory around the sun, potentially sending our world spiraling into the stellar furnace or casting it into the frozen darkness of interstellar space. Humanity's long-term survival prospects add another layer of uncertainty to this cosmic speculation. Our species has existed for only a tiny fraction of Earth's history, and technological civilization spans mere millennia compared to the billion-year timescales relevant to galactic evolution. Biological evolution, environmental changes, or technological transformation could render future Earth inhabitants unrecognizable compared to contemporary humans. Advanced civilizations might have spread throughout the solar system, neighboring star systems, or even distant galaxies by the time of the cosmic collision, making Earth's specific fate less relevant to humanity's ultimate survival. The witnesses to this galactic merger might observe from artificial habitats orbiting distant stars rather than from our ancestral planetary surface. Yet the possibility remains, however remote, that Earth could somehow navigate all these existential challenges while maintaining stable orbital conditions throughout the merger process. In this optimistic scenario, any surviving inhabitants would experience one of the most spectacular astronomical displays in cosmic history. The approaching collision would unfold over millions of human generations as Andromeda gradually dominates increasing portions of Earth's night sky. Eventually, the neighboring galaxy would appear as a brilliant tapestry of stars, gas clouds, and dark dust lanes stretching from horizon to horizon, a celestial display requiring no telescopic assistance to observe. The merger's climactic phases would trigger massive star formation episodes throughout both galaxies, creating brilliant stellar nurseries that illuminate the night sky with unprecedented beauty. These cosmic fireworks could persist for millions of years as gravitational compression ignites stellar birth throughout the combined system. The central black hole merger itself might remain hidden behind vast clouds of infalling material, but its influence would manifest through powerful jets and energy bursts as matter spirals toward the combined event horizons. These outbursts could temporarily outshine every other star in the merged galaxy, creating transient beacons visible even during daylight hours. However, the stark reality suggests that Earth will likely have succumbed to solar evolution, gravitational ejection, or countless other hazards long before this cosmic celebration occurs. The universe operates on timescales that dwarf biological evolution, and the forces shaping planetary fate rarely accommodate the convenience of potential observers. Our exploration of Sagittarius A star's nature and destiny illustrates the profound interconnections linking the smallest scales of human existence to the grandest cosmic processes operating throughout the universe. From Carl Jansky's accidental radio detection to the Event Horizon Telescope's revolutionary imaging, humanity has gradually unveiled the monster lurking at our galaxy's heart while developing technologies that push observational capabilities toward theoretical limits. This journey from mystery to understanding demonstrates how sustained scientific inquiry can eventually illuminate even the most exotic phenomena in nature. Each generation of researchers built upon previous discoveries while developing increasingly sophisticated tools for probing the universe's most extreme environments. Sagittarius A star continues serving as our most accessible laboratory for studying fundamental physics under conditions impossible to reproduce on Earth. Its gravitational field tests general relativity in regimes where space-time curvature reaches maximum intensity, while its magnetic environment reveals how matter behaves when approaching the ultimate limits of density and temperature. The black hole's influence extends far beyond its immediate vicinity, shaping galactic structure across billions of years while regulating star formation through complex feedback mechanisms that connect the smallest scales of stellar birth to the largest scales of cosmic evolution. These relationships illustrate how supermassive black holes function as cosmic architects, constructing the framework within which galaxies develop and mature. Future observations promise even more remarkable discoveries, as technological capabilities continue advancing toward direct movies of matter spiraling around event horizons. The combination of space-based interferometry, gravitational wave detection, and multi-wavelength coordination will create unprecedented opportunities for studying black hole physics in real time. The approaching collision with Andromeda Galaxy represents the next major chapter in Sagittarius A star's evolutionary story, an event that will transform our quiet galactic center into one of the universe's most energetic phenomena, while creating a supermassive black hole capable of anchoring galactic structure for countless billions of years. Whether humanity survives to witness this cosmic spectacle remains unknowable across the vast timescales involved, but the physical processes governing these events operate according to scientific principles we can study and understand using current observational capabilities. The universe continues revealing its secrets to those patient enough to observe and clever enough to decode the messages hidden within electromagnetic radiation and gravitational waves. Sagittarius A star reminds us that the cosmos contains phenomena so extreme they challenge our fundamental understanding of reality, while simultaneously confirming the predictive power of physical theories developed through careful observation and mathematical analysis. The monster at our galaxy's heart represents both ultimate mystery and scientific triumph, a cosmic laboratory where the universe's most fundamental laws operate at their absolute limits. The story continues unfolding as new instruments come online and analysis techniques improve, ensuring that future generations will inherit even deeper understanding of the gravitational extreme that has anchored our galactic home throughout its entire evolutionary history. Each discovery brings us closer to comprehending our place within the cosmic architecture, while revealing new questions that will drive scientific inquiry for centuries to come.